that is in place. Yes, so if it is Wi-Fi, if the frame needs to be delivered over Wi-Fi, the frame will look different to the frame that will be used to deliver across Ethernet link. Yeah, so it's just, this is the task that will layer 2 will be involved into. Yeah, so it will encapsulate into appropriate frame, and also it will be looking after error checking, right? So the frame will be there is a trailer, so the frame looks like this. There's a data, there's a layer 2 header, header, and then there is a trailer. So in this trailer there is some sort of a easy, quick algorithm. So it's a frame check sequence, or and we'll come to this. We haven't looked at what the name of that is, so it will come in the next module. But anyway, it's the idea of the trailer is that there is some sort of a quick algorithm. So this can be calculated, put through that algorithm, and a certain number will come out as a result of that calculation, and this number will be included as a trailer and by the sender. So this guy wants to send, well, this device wants to send something, and it will include that number as a check. Yeah, so it's a check for errors, because when the frame is delivered, and then the receiver now will put the same data through the same algorithm, and then if it comes up with the same result, same number, it will mean that delivery was successful. So there are no errors. But if the number is different, it means that data somehow been changed during the transmission, and that will be rejected, and it will be recognized as some sort of a corrupted delivery. Yeah. So data link layer is split into sublayers. So one is facing upwards towards the logical protocols, yes, the software protocols above layer 3, and it will be aware of what protocol is being used in layer 3. This is a layer 3, right? And layer and max sublayer will be facing towards the physical layer. So this is logical link control. Yeah, so logical facing towards, well, up. Yeah, facing towards the upper layers, and the max sublayer is the one that will be aware about physical. So if this is Ethernet, so it will obviously it will frame it differently. Yeah, if it is wireless, and so on. So max sublayer is responsible for data encapsulation and media access control. Then we looked at how it works. So at each hop, so hop means it's the router, isn't it? Routers will do this kind of job. So router at each hop along the path. The path can be long, can be short, it doesn't matter. So each router along the path will perform what? It will take the frame which is delivered from whichever medium is being used. If it is Wi-Fi frame, then it will accept that, de-encapsulate, remove all the data, all the encapsulation, and look at the packet, check the IP address where it needs to go, and the packet won't change, right? The router will not change the packet, apart from one small thing which will be changed, but we will look into that a little bit later, and then when we talk about layer 3. but IP addresses won't be changed. That's important. So the where it needs to go, the final destination, that routers along the path will not alter. They will not change any of that. But the frame, yes. So the frame will be accepted, de-encapsulated, and so this is the router, right? It comes here as a frame with a header. This is a layer 2 header, right? So this will be removed. This will be left intact. And when it is being sent out from another interface now, and so this bit, data bit, yeah, so this will be left as it is, and a new layer 2 header will be added, which is appropriate for this part of the route, yeah. And then until it reaches the next route, or maybe there's another destination, if it is the final destination. But still, routers will perform this until it is delivered to the destination, right? So the some organizations that look after standardization of this. So IEEE, so your Wi-Fi, Ethernet standards, they will come under IEEE, Institute for Electrical and Electronic Engineers. All this 802.2, 802.3, 802.11, which is your Wi-Fi and different flavors of it. Yeah, they all are standardized by this organization. So then we looked at physical and logical support topologies. So physical is how your devices are actually physically connected. So you've got a cable, you plug it into device, and this is your topology. Yeah, so this is you follow the physical connections, right? So you've got a switch, you connect it to a computer here. This is your physical topology, right? So you need to look into that. But then you might somehow disappears. I don't know what's going on. I think it's the edge of the screen or something. So, and this is your physical. Yeah? So you've got this. The way you connect your end devices to the switch is called a star, because this is like in the middle, like a star with some rays, yeah, coming away from the star. So it looks like a star. Then you've got if you want to extend this, you can add another switch and you can have an extended star, right? There's another switch and it has more end devices connected to it. So you can have it as an extended star. And logically, yes, sorry, and logically you can, so this is physical topology, and logically you can split it any way you want. Yeah, so you don't have to follow logical topology. So physically you can put these 3 devices into one network, yeah, subnet, and this will be in another network, for instance. So this will be your logical topology. So point to point, yeah. We're talking about one topology. So point to point is the simplest. So one device and on one end, and there is another device on the other end, and there are no other participants there, right? So there is no one else on that link. So hub and spoke. So this is like a star, similar to a star, but so you might. So if this is your H quarters and you've got branches, right? So this is your hub and you've got branch 1, branch 2, branch 3, and this is hub and spoke. And mesh, you can, when you connect everything, all the nodes, you connect, have a connection between them, right? So or you can have a partial mesh. Partial means if you have almost all, it's not a hub and spoke, but it's not full mesh, right? So it's like this would be counted as a partial mesh. Even this will be partial mesh. This is hub and spoke, but then you connect two branches directly. This is your partial mesh, right? Point-to-point. So physical point-to-point topologies directly connect two nodes. They may not share the media with other hosts, right? So there are no other, anyone is part of this communication. And because all frames on the media can only travel from, well, there is no other way. They can, if something is sent from node 1, it is definitely going to node 2. There are no other destinations, right? So LAN, yes. So star, extended star, and this is how it all started. We don't use it anymore. This is a bus topology. So just single cable in the middle and permanent connections to that cable. And this is a ring topology. This is legacy as well, obsolete. We don't use it anymore. So in these topologies, well, even in that topology maybe, but how it started, yeah. So they used to, all the communications were broadcast. So if this guy wants to send something to this guy, it would go everywhere, right? So this was broadcast, and by so this is a multi-access network, yeah. So there's multiple devices, and so MAC address becomes very important, right? So the destination. So you have to state to which device the communication is going. So the receiver will check and will accept this communication. Others will receive it as well, but they will drop this to say it's not for me. And ring topology is when one device gets its turn to transmit. So if this guy has a token, right, it has a and then it will so this guy, and it will have a turn to transmit whatever it wants to transmit. It may need to transmit it here, for instance. All others will wait until they get the token. This is the way of avoiding any collisions, right? So whoever gets the token, they have the right to transmit. Yeah. So half duplex when communication happens in one direction only, and this is what we used to have in legacy bus topologies, and we still use in wireless LAN, yeah, in Wi-Fi's. And with switches, we have full duplex communication. Communication happens in both directions at the same time. Carrier sends media multiple access collision detection was the original one when the like on bus topology. That's what they used to have, and so they would sense there is a collision. So basically, yeah, if two devices transmit at the same time, it shouldn't happen. But if this is the case, then it would create a collision, and all the communication would have to stop and wait until the collision is cleared, and then retransmission would need to. Data would need to be retransmitted. With the collision avoidance, that's what we still use in Wi-Fi. A device needs to send a signal, and it will. I would like to transmit, and this is my intention. I would like to transmit for, and my transmission will take this long, and when it is given a clear signal to transmit, it will transmit for this long, and everyone will know that for that duration there is the media will be occupied. Basically, they mustn't transmit anything at this time. So this is contention-based access, and controlled access is in your token ring networks. Yeah, and there is something which is called ArcNet. This is obsolete. We don't use it, right? But the idea is that someone gets this token and they transmit, and everyone will know it's not because they don't have a token, so they know they have to just shut up for a while, yeah, until they get a token. So yeah, so this is CD collision detection. This is legacy Ethernet LANs, collision detection process. How it happens. Device will, if this is collision, devices will wait a random period of time and then retransmit data. Collision avoidance. So yeah, this is your Wi-Fi. We still use it, believe it or not. So how the collisions are avoided, because yeah, so basically they will when transmitting devices will include when they get a clear signal, like a permission to transmit, yeah, and they will announce themselves that they need to this much time duration they need for transmission, right? And so in Wi-Fi usually there are no collisions, and the reason is being because if there is a collision, so it would be difficult to detect it, right? So collision detection wouldn't work because there's Wi-Fi on the same link, on the same wire, on the same cable. This is possible, but on wireless, it wouldn't devices wouldn't know if there is a collision or not. Yeah, basically it's collision detection wouldn't work there anyway. Right, the frame. That's where we stopped, I believe, last time. So it was just a little recap, quickly. Data is encapsulated by the data link layer with a header and a trailer to form a frame, right? So data link will have three parts. A header, this is added by layer 2, by data link. The data which will be given to data link layer by the above layer, and a trailer with error detection, which will be used for error detection. Yeah, it's called frame check sequence. So we've got 27 people. I think it's a record for this class. Yep. Okay. So the amount of control information carried within the frame varies according to access control information in logical topology. Yeah, so let's look at the frame, right? So this is interesting. So frame will look, so if one device, like here, this device transmits something, and it will be a stream of zeros and ones, right? And it will be multiple frames, one after the other, one after the other, one after the other, right? So they have to be separated somehow. So the frame start and frame stop will be there, delimiters, right? So frame delimiters. Usually they don't count as a part of the frame, but they are obviously they're there. So then after the frame start will be addressing. So this is the actual header. So the addressing destination and source and type of the protocol that is being used from in the right. And I think this is a new person. Give me a second. Sahil, hello, good morning. Or is it sorry, is it Sahil? Is it my colleague Sahil? Sahil, hello? Who is Sahil? Sahil? Sahil, good morning. Right. Anyway, so type will be included of this will indicate what protocol above from layer 3 was used. So if it is an IP version 4, IP version 6, or there are some other protocols there. Layer 3 could be used, right? But IP, yes, so usually it's IP version 4, IP version 6, depending on what IP protocol is in place. Then the data itself, the packet, then error detection, trailer, and then the frame stop. So indicate where the frame ends. So layer 2 addresses, yeah, so MAC addresses, as we call them, or sometimes they're called physical addresses, or sometimes they're called burned in addresses. And the reason being because they are given to any network interface card. So if you have a laptop, it has a network interface card, maybe probably Wi-Fi. But if it has an Ethernet port, then it will have two network interface cards, one for Wi-Fi, one for one Ethernet card. If you have routers, they will have the interfaces. Each interface it is a network interface card, right? So it is a separate adapter, yeah. So it's a separate interface, and each and every one of those will be given as a unique MAC address or physical address at the time of production, right? So each network interface card, when Samsung or HP or whoever makes your network interface cards, or Broadcom, they will assign a unique MAC address, which will be used. This is not changeable, right? So this remain the same for the lifetime of that product, of that device, of that adapter. Yeah, hello. Someone has a yeah. Ethernet port. Yeah. Yeah, of course. Yeah, there are different network cards, so they must have separate MAC addresses. Yeah, it's not the same MAC. It's not the same card. So your laptop will be identified twice. So you can join two networks at the same time. Yeah.
This is one of my same thing popped into my mind as well. So which one get is that like if you have Wi-Fi and LAN wire connected,
Yeah.
which one gets prioritized? Like is it a Wi-Fi or the
Well,
the
that's this is this is we're talking about Windows.
oh
I
yeah,
don't know,
Windows
operating
here.
system. Yeah, operating system. But well, what do you mean prioritize? So it needs to,
The
yeah.
both connected to the internet. The wireline and for example
I think
wireline and the wireless
There
line.
I
is a
think it's the
setting
wire.
somewhere in Windows, so you will go into your network to your control panel somewhere, and
Okay, got it. Maybe you can't
what?
prioritize it. Okay.
Yeah, so it's in control panel somewhere, and then you will need to go to network sharing center. So I've got two. I've got so you change adapter settings, and I've got quite a few. So I've got where is my Wi-Fi? So I've got the Wi-Fi. So it's you see it's not connected, but I've got Ethernet, which is connected. So you can
Yeah.
prioritize them. Yeah. So it's it's up.
Val,
Yeah.
hi. Sorry. You mentioned that if you laptops normally come with to anyway, generally, but you said you can connect to different networks or to routers at the same time.
Yeah.
But you can know how is that done? Because as far as I'm aware, I've got a Wi-Fi and an Ethernet port on my device. When I plug in my network cable, it turns off the Wi-Fi, and when I take out the network cable, it goes on to Wi-Fi. But how can I get them both to
Well, so
function at the same
let's
time?
say you've got your laptop, right? So you've got a laptop and Wi-Fi. You can connect to your router, wireless router, and you've got an Ethernet port cable. You can connect to your desktop computer, and this will be different networks. So this will take you to internet, and this will be your local connection, just sharing something with your desktop. So you could have it as a not okay. Maybe desktop there is no point, but for instance, if you have a if you ever decide to go and set up your Cisco lab, right? So you want to buy Cisco equipment just to have it in your home and practice. So let's say you've got a Cisco router here, right? And you can connect to the Cisco router, and then you can use and then you can set up your lab. So this will be your switch. It'll be probably another router here, something like that. This will be your switch. So here you've got one. I don't know. You will have one. So your home broadband network will be defined by this home router. Yeah, this is home router, broadband router, and this will be most likely something like that, 0.1. Yeah, so this is the address. But here you can I don't know, you can assign any private address you want. So 172.16, I don't know, 10. This will be your network address, for instance. So this two separate networks, and you can so you can connect to your router and configure it over the network, and at the same time you will be connected over Wi-Fi to your internet, to your home router, home broadband. It is possible. I mean, maybe it's not, yeah, because you, I don't know, if you've never done it, maybe it's seems a bit complicated, but it's quite easy to do. And you're saying that if you have competing, so if you have if you try to basically, yeah, what your predicament is, I understand. So if you have the same link, well, not the same link, but the same destination. You've got the same broadband router, so you can connect to it over Wi-Fi, or you can have it now a cabled connection to the same router, and then basically you've got now two links to the same device, to the same router, and this may switch off your Wi-Fi, and if you plug the cable in, right, so it might take over. I think that's what happens normally.
Correct.
But this is the Windows feature. Yeah, so this is up to Windows to decide. So they must have, the Windows have this I don't know, feature, if you like, which will sense that you've got two links leading to the same device, to the same router, and it has to choose one. So it will choose cable, Ethernet over Wi-Fi.
Okay. If it's a separate device, like as you said, another Cisco router, that would
Yeah.
treat it separately and that would be different. But if it's to go into the same device, it kind of gives you priority to the Ethernet.
You can't use both, yeah, because it just doesn't make sense.
Okay, cool. Thank you, sir.
Right. So MAC address is something which is given to a network interface card, and this will be the permanent identifier, right? ID of that network interface card. So when router 1 sends something to router 2, it includes its own MAC address, or not own, but its interfaces, which is connected to router 2, a MAC address, and sends it to MAC address as a destination, to MAC address of that NIC, right? So this is the source, this is destination, yeah? So the MAC addresses are being used for this purpose. And so this mechanism, these MAC addresses, they are being used only for local delivery of a frame on that link. So on this link only, yeah, this will be the source and this is destination. When it comes to router 2, remember, it will remove all this frame, it will encapsulate the frame, remove the header, and on this link, it will put now this source, and this is destination MAC address, yeah? So of this NIC and that NIC. Yeah, so so the MAC address is only valid on the same link from router to router, or from router to the end device, to the server, or from here, from this source end device to the router.
Pavel,
yeah.
can I ask another question, please?
Yeah.
I was looking at this a little bit yesterday and today. I understand that. Okay, so when you send something from the source to the destination, at each point it decapsulate and then encapsulate with the new MAC address of the router and then so forth. Yeah.
Yeah.
When it gets to the final destination, it does the same thing. So it decapsulates and removes the NIC address of the router 2, for example, because it doesn't need that anymore because it's at the source.
Yeah.
Now at the destination, but now when it's going back, now imagine this is the source is like a home device, yeah. So it's gonna have a local router IP address 192.168, yeah.
Yeah.
It keeps the IP address in that packet, right, of the source.
Yeah.
But the IP address of 192.168, that could be for any computer in the world.
Yeah. You're right. Yeah. So yeah, I understand what you're saying. So router 1, so your local router here, your local home router, yeah, it will replace your. So here you've got 192.168, yeah, which is private IP address, yeah, and it will replace it with something which is your public IP address. So remember last time, I think it was last time, we looked at your, and you can do this now if you like. So you can Google for what is my IP, right? And it will show you your public IP. So this is my public IP address. I'm shown, I'm in Norwich somewhere. Well, I'm not, yeah. Yeah, city Norwich. But so it means that my ISP somehow shows me as a Norwich. So they probably have some sort of a node there, but it doesn't matter. What it matter? What your question is about is when we use private IP addresses, like 192.168, whatever. Yeah, yes, you're absolutely right. So there are millions, or if not billions, devices that will have the same IP address privately. Private. So this is the difference. So this is the private IP address. It will never be routed on the open internet. So it can be only routed. Internally on the internal network. So here, perfect. Yeah. So this is private area. This is your domain. You do whatever you want. But the moment it reaches your router 1 will do something which is called network address translation. We will look into this at the later stage. So this is the way Cisco likes to present things one step at a time. So yes, you're absolutely right. NAT will have to be in place, and it will. So your private IP address, like that, will be replaced with your public IP address, which is in my case. Let me just. So it's 92.54 whatever. Yeah. So 92.54. 232.242. This is my public IP address of my entire network. Yeah. So on the outside here, on the outside, my router 1, this is my home router, will use this 92.54 whatever. Okay. So yes. So it's not exactly right to say that the IP address will remain the same from the source, I guess that was your question, to the final destination, right? Because of this NAT translations. So it doesn't apply to IP version 4. Exactly. But if, for instance, if you have IP version 6 addresses, so if this your device has an IP version 6 address, then it can and it will remain unique. So it doesn't need NAT services of a NAT network address translation like IP version 4. IP version 4, remember the reason why we use this separation into private and public IP addresses, because there isn't enough of IP version 4 addresses for everyone to have. So you have to carefully manage those IP version 4 addresses and give them to whole bunches of devices. So if one company wants an external internet link, it will sign a contract with internet service provider, and it will public IP address will be allocated to the entire company, entire organization, which will be shared among all the devices that will be within that company. Yeah, within that organization. So if you have another device here, and they're all connected to this router, right? Somehow. So all these devices internally might use 192.168, I don't know, network 10, for instance. Yeah, and this will be 3. This one will be 0.4. This guy is 110. But when they reach this, they all will be translated into that single public IP address. Yeah, so public IP address. There isn't enough of those. There's a scarcity of those. So whatever it is, 154, I don't know, 242, whatever it was. So you can just check out your own public IP address. And so this public IP address will be shared among all the devices. If there is hundreds of them, all hundreds, all of them might share the same public IP address. Okay, so you are absolutely right. So it's not entirely true to say that IP address will remain the same from the source to destination. But the idea is, because if you use, as I said, if you use IP version 6, then this guy will have unique public IP address, and this guy will have a unique public IP version 6 address, and then this will work. Yeah, so this idea that there is no changes to IP address from the source to destination will apply. But with IP version 4, it doesn't, because it's because of this mechanism, yes, of translation public into private. But let's not get into there, because it will just complicate things for you, right? Just remember that usually, yeah. So the routers, yes, after the NAT, so NAT will happen here somewhere, and this router, because it is local to this, it will do the NAT as well, unfortunately. But if there are some bunch of routers on the way here, maybe not one, but a bunch of them, yeah. So then these routers will not get involved. But also it also will work. It also will work, this idea of not changing the source to source and destination IP address from the source to the destination along the entire route. This will also work if there is no need. So if, for instance, this all are part of the same internal company network, like intranet, right? So if there is no, so if this router is not a link to public internet, yeah, open space, where public addresses have to be used. So if all of these devices are part of the same internal organizational network, then this principle will apply, right? So this will be sent here, and this router will not do any NAT translations, right? It will send it to there, and then it will eventually come to the server. So if this is your internal company network, company server, whatever it is, then this principle will apply. It doesn't need to. So NAT will not be in place here because nothing reaches outside. Nothing goes leaves the realm of internal organizational network. Okay, so this principle will apply of not changing IP address from source to destination. Is this?
Yes,
Does it
Pavel,
help?
you answered the question.
Yeah.
Thank you. I was just knocking my brain about that and thinking, oh, that makes sense. So yeah, but, thanks for clarifying. You did mention that before, early on in the course, and I obviously forgot about that. So it's good to have the recap.
Yeah, we'll come to this, and not translations will come to this. They will come. Yeah, but for now, just let's assume there is no nothing of this sort is needed, and then let's assume that this is the principle and everything works like that. So, and as I said, it does work like that if all these devices are part of the same internal network, so nothing leaves and goes into public open space, open internet. So yeah, so the logical topology and physical media determine the data link protocol used. So LAN and one frame. So depending on if it is an Ethernet or wireless 802.11, if it is a point-to-point protocol, this we call it serial links. Yeah, so they will you will see the serial links in packet traces, or maybe HDLC or frame relay. So it's just some protocols. How these are one links. Yeah, so links between sites. So if you have a branch to the headquarters, so the frame relay might be in place, and according to the so if you use this protocol, the frame will look different. It will contain so it will contain some information which is relevant to this protocol, right? If frame relay protocol is in place, then the frame, the header, which will be attached to the packet by the data link layer, will look different to HDLC. It will be relevant to frame relay, so the information will be included, which will help this protocol to deliver the frame, right? So what is needed for that frame to go from one router to the next router will be included in here, right? So in the header, which will help this process. So yeah, so for each this protocol, one kind of a frame, this protocol, another kind of a frame, this protocol, another kind of a frame. We're not looking into any of those frames, by the way, and these protocols are kind of obsolete anyway, right? So we're not using them much, maybe somewhere, but and for that reason, we're not going into details anyway. Yeah, and each protocol will perform media access control for specified logical topologies. And so they will basically they will include. So what is media access? They will include the information in the frame that is needed for the frame to be delivered over that protocol and over that logical topology as well. Yeah, so the frame, basically the principle is just frame needs to be adapted to what is being used, right? So it will include relevant information and that's what the main kind of idea that you need to take home from this. And I think that's it. So there isn't much really to talk about, really. Let me just check. This person just came in. Yeah, so we've got this new person just logged in, Yashokini, Jasokaran. Hello. Yeah, Mohammed, you've got, yeah. Have you registered, Mohammed?
Yes, I did. Yes, I did.
Can you put your email address in the chat, please, so I can
Yes.
add you to the class? Yes, yeah. So Yashokini, Jasokaran, hello, and Sahil, hello. Hello, are you here? It just looks like ghosts. Oh, Jasokaran, have you registered? I don't understand. Have you registered with Netacad?
He said no,
No.
not yet in the chat.
Well, so there's no use to give me this email address. So you need to register. Okay, so please go to this netacad.com and please click on the and please can you communicate? Oh, there's another person, Jeffrey Baron, right? Yeah, Jeffrey, hello, good morning. Can't hear you. You need to switch on. Just okay. What is going on? So Yashokini, I hope I pronounce your name correctly. Can you please go to this, click on this link, and it will take you to login screen. You need to log in, click on login. Next screen will show you, because you don't have an account, so it will ask you to sign up. And this is where you need to register. So you need to provide your full name, register basically with that Network Academy, which we use to study, right? So it is essential for you to register there. Mohammed, you still have your arm up. Let me just put you in the class. So your email is this. Yeah, Mohammed Sharif. Good. People who spell your names without capital letters, with all lowercase, your certification will look like this. Yeah, so so if you spelled it Mohammed with all lowercase, it will look like Mohammed without capital M. Yeah, I mean, I'm just saying it doesn't matter to me at all. But if this is something you would like to have, no problem.
No, I'll do it the right way. I'll make it capital letters.
Yeah, I mean, it's just up to you because.
Okay.
So Yashokini, or Jasokaran, I don't know how to pronounce it correctly. Have you registered? Okay, let me just copy this email and try to add you here and see what happens. Oh, yeah. I can see that the last name is slightly different. This is your full name. Yeah, as I said, your certification will come to this name that you stated here. Is this how you want it to your certification to look like? Hello? I don't know.
Hello. Sorry.
Yeah.
Can you make mine capital letters if you on your side?
No, I can't.
How can I make? I have to go to back and then edit it.
Yeah. Yeah.
All right, I'll do that.
Anyway, it seems like a one-way street communication. Anyways, right. So I've added two of you, and Sahil, are you with us? Who's Sahil? There's no email. This person doesn't have a Teams account. Lovely. Right. Okay. Let me just switch to next module. This is module 7. So let's talk about Ethernet switching. So yeah, frames will be added by data link layer by all protocols, but we're going to focus on Ethernet, yeah, because that's what we to use. Slideshow. Yeah.
You're not sharing the screen?
Yeah. I'm going to share. Just give me a sec. There you go. So Ethernet, right? Oops. Just I'll share again. Just give me a sec. Something happened to my PowerPoint. It used to skip. There are a couple of usually slides which are not meant to be shown to you guys. They're meant for instructors. It used to be work like you click and it would skip those. When I present, it would skip them, but now it doesn't. I don't know why. So I have to unshare and reshare. There you go. So Ethernet switching, right? So Ethernet is a layer 2 technology, right? So protocol, and we're going to look into that. So we're going to look at Ethernet frame in more details, not like generic like we did in previous module, and we will look at MAC addresses. So MAC addresses, for instance, when it is a point-to-point protocol, right? So MAC addresses are not being used. So for Ethernet, yes, right? So if it is an Ethernet frame, it has to, because Ethernet by default is a multi-access network. But if it is a point-to-point, there is no need to include MAC address, because if the sender sends to the destination, well, there is no other destination available, right? So there is only one destination. There are two devices talking to each other. So there are only two of them on the same link. So in this case, MAC addresses may not be used. They are not needed. But for Ethernet frames, yes, MAC addresses are essential, because otherwise, if that would be a mess. Yeah? No, everyone would receive and accept that frame. No, it wouldn't just work. Yeah? They wouldn't accept anything. It would just be. It wouldn't be just possible. So Ethernet MAC address. Yeah. So we're going to look at MAC addresses. Then we'll look at MAC address table. How switches build MAC address tables and how MAC address tables are being used to help deliver the frames. And then we'll look at different speeds of switches and different forwarding methods. So Ethernet frames, right? So they are data link layer 2 frames, but obviously they're related to the physical, because physical layer, you're going to use Ethernet, right? So Ethernet cables, and that's what determines which layer 2 frame needs to be encapsulated, right? So if you use Ethernet technology, Ethernet cables, so you plug your Ethernet cable into your port, and then because of the physical quality, yeah, the layer 1 physical layer is being used Ethernet, so the layer 2 has to be frame has to be suitable, yeah, for that particular medium. So obviously they are related, and So Ethernet operates in the data link layer and the physical layer. It is a family of networking technologies defined in IEEE. And so 802.2 is logical link control protocol, and this is the actual Ethernet, right? So for physical and max sub layer. So data link is split into two sub layers, and one is LLC, logical link control, and the standard is defined in IEEE 802.2, places information in the frame to identify which network layer protocol is used for the frame. Right, so basically the frame will contain a type, remember type, so the type will say this is the above layer is IP version 4, or above layer network layer is IP version 6. And max sub layer, so it could be 802.3, which is Ethernet, this is your wireless, Wi-Fi, and this is your Bluetooth. Right. So max sub layer will be responsible for data encapsulation and media access control, provides data link layer addressing. We already know this, yeah, from previous module. So according to well, if Ethernet can be also different, right? So it can be gigabit Ethernet, fast Ethernet. So initially the Ethernet itself, when it appeared, yeah, Ethernet, we call it this speed, right? 10 megabits per second, which is not much. Right, so it's not much. And then
Hello?
hello.
Yeah, I done it with the NetCat and registered with that now.
Oh, okay.
Yeah.
I think I put you in, but can you tell me, you registered under different name. Which one are you
Yes,
using?
my first name, Yasoharan Manikam.
So how would should I call you? Yasokaran?
Oh, yes, please.
Yasokaran. Okay.
Yeah.
So, okay, good. Yasokaran. Okay, good. At least we can talk now. Yeah.
Yeah.
So Ethernet is the original Ethernet was 10 megabits per second. Then they came up with fast Ethernet. So even though it's called fast Ethernet, and you will see this a lot in when we come to the switches. And if you remember, did we do this in module 2 when we did basic configuration? I think we didn't touch anything. We didn't do anything related to the ports themselves. But anyway, when it comes to configuring Cisco switches, you will see lots of that, right? So fast Ethernet is 100 megabits per second, and there is a gigabit one, yeah. Well, that's easy, right? That is 1,000 megabits per second or gigabit per second, yeah. So this is Ethernet. So this is fast Ethernet, and obviously as this progressed, this technology Ethernet progressed from first introduction to Ethernet to fast Ethernet, and then gigabit, and these are different standards. Like with your Wi-Fi, right? So you've got one Wi-Fi, one generation, then they introduce a new one, and then they as the technology improves, being developed, and then the protocols, there are new protocols which need to be put in place, so everyone follows the same protocols. Yeah, so if there is a new technology, so it has to be standardized, and so IEEE will issue a new protocol. So there's new variety, kind of, yeah. So usually it's like with Wi-Fi, you must have seen the Wi-Fi, like they have A. Yes, they've got 802.11. They must have seen A, B, AC and whatever. Yeah, there's Z. There are lots of letters now. Right? They all identify different flavors of Wi-Fi, different, and they're under the same umbrella, 82.11, but they are kind of different. So if you have a device which is not capable of the latest Wi-Fi, it's not aware that there is. So if you have a device from 10 years back, it wouldn't be able to use the protocols that modern devices will be capable of, right? Because they're different protocols, different rules. It's the hardware is not it's not capable of that, right? So and the same kind of with Ethernet. Any really technology, isn't it? So the protocols need to be adapted with the progressing of those technologies. So max sub layer, the second kind of, there is an LLC sublayer and max sublayer. Max sublayer, the bottom sublayer, is responsible for data encapsulation and accessing the media, meaning that yes, different media, accessing different media would mean different things. So for Ethernet 802.3, this is Ethernet number for Ethernet protocol. So 802.3 data encapsulation will include Ethernet frame itself, so how it's supposed to look like, and what has to be there. That is also part of the protocol. Ethernet addressing, so what needs to be included, so source and MAC and destination MAC addresses to deliver Ethernet frame from one NIC to the other on the same LAN. Remember, on the same link, and Ethernet error detection, that is included in a frame check sequence in the trailer, and will be used for error detection. So 802.3 max sublayer includes the specifications for different Ethernet communication standards. According, so it could be, you can see here now we're looking at different flavors. So there is one U, which is fast Ethernet. There is Z, which is gigabit Ethernet over fiber. So Ethernet can work not only over copper wire, but it can only also work over fiber. Yeah. So, and that is a Z flavor of this of Ethernet. AB is the gigabit Ethernet over copper. This is what is common now, right? That's what your home devices, your laptops, I don't know, your desktops, if they have Ethernet ports, they will probably have something like that. Yeah, it's been there for a long while. Gigabit. Okay, let me just. This is just Jeffrey. Hello, good morning. Jeffrey.
Good morning.
Yeah, good morning. Yeah. So are you new?
Yes.
Right. Have you registered yourself with Cisco NetAcad?
Is that the 5E? No, I went for my assessment yesterday, and the lady said to me she would email me with regards to starting the meeting today. But basically, I didn't receive no emails. I was checking my emails up to this morning, and I didn't receive an email. Then my phone started ringing, and they were saying to me, "Oh, we've sent it. It's been sent to you. It's been sent to you." And then the lady sent it to me via a message on my phone. So
Okay.
I've just managed to sort it all out to get in to speak to yourself.
Okay, good. But my question is, we all are using something which is called NetAcad.
Okay, no, I'm not registered with that yet.
You haven't. Okay, so so let me just put a link in the chat. Give me a sec. So you need to go to www.netacad. Can you access the chat? Are you able to?
Yes, I should be able to.
Yeah. Can you click on the chat?
Hold on. You'll join team feed team.
Are you using Teams
Yes.
app or web browser?
I'm actually using the app on my phone at the moment because I wasn't
Oh,
sure what was going on, so
okay.
it's going to be a bit awkward. Here we are, chat.
Yeah.
Yes, I can see it there.
So click on that NetACAD, on that link. Just click on
Yeah.
it, and it will take you to the to a web page. Yeah, and there it will. They will ask you to log in. So click on login.
Never can. Hold on. I'm just waiting for it. Can start learning.
Login somewhere. Top. I don't know how it looks on mobile, to be honest, but probably.
So I found it. Yeah, login.
Found
Welcome.
it. So click on login.
Yep.
And because you don't have a login, so it will ask you to sign up. You need to sign up, register yourself.
Okay. Account. Okay, where's it gone? Oh, continue with Google. Do not sign up.
Yeah.
Yeah.
So click on sign up and follow. It's quite easy process. So
Yeah.
Register with your email and provide your full name, like first, second name, and please use capital letters and don't make any spelling mistakes, because that's where your certification will come from too. So your email address will be your identity with NetACAD. And
Okay.
also, if you provide, if you misspell your name, the certification will come to that misspelled name. Yeah, so
Yeah.
be careful.
Okay then.
So when you finish, let me know, and can you put your email address in the chat so I can put you in the class? Yeah, it will give you access to all the materials.
Okay then. Well, I'm
Alright.
Yeah.
All
Okay,
right.
I'm gonna do that now.
Yeah, please. What did you do with 5E? What have you just finished? Is it cybersecurity?
I haven't. No, I've just signed up. I've just recently signed up with them, so I haven't done any. I haven't done no courses with 5E before.
Okay, that's fine. So, right, yeah. So, so Ethernet can work over various types of media, including copper and fiber. Right? It doesn't have to be fiber. It doesn't have to be copper. It can be fiber as well. So just bear it in mind. So it's not just copper wire. So legacy Ethernet using a bus topology or hubs is a shared half duplex medium. Yeah, remember bus topology. And Ethernet over half duplex medium uses a contention-based access method. Carrier sense multiple access collision detection. Right? We talked about it just today and last session. So if one device transmits something and others have to listen and to be careful not to stop transmission at the same time. If they do, there's a collision. And then this has to be cleared, and everyone has to wait, and then start retransmission. This we don't do anymore, right? So this is legacy in Ethernet, but it can happen sometimes. There are somewhere maybe some areas of some old networks that might still use this legacy Ethernet because of some complications of upgrading. Yeah, so apparently there are some military sites and some like health in health. If there is a equipment which was, I don't know, introduced in 1980s or maybe even 90s, and it was meant to use this, and it's difficult to change it because you can't, right? So you have to replace the whole unit, and it costs like, I don't know, costs too much to replace, and they still have to use that old technology. So you can come across, but generally no. Yeah, so generally it's not something which is it's not a technology of choice. And so Ethernet LANs of today will use switches that operate in full duplex. So that's why we like switches, because it's not, I mean, you can improve switches, you can make them faster, but the principle of switched networks do not change. We still use switches. They were introduced some time ago, and they are just brilliant. Yeah. And Cisco is the largest company that makes switches. Yes, so, networking equipment. So they're number one. Ethernet switches do not require access control through CCNA/CD. Like, okay, that's the basics, right? So let's look at the frame, how it looks like. This usually doesn't come. It doesn't count it as the towards the size of the frame. So the size of a frame is anything between 64 to 1518 bytes. Yeah. So this is the minimum, and this is the maximum. There are some exceptions, and some frames can be. There are some jumbo frames, but as a rule of thumb, so the frames should be anything between 64 bytes and up to 1518 bytes. Yep. The preamble field is not included when describing size. Any frame less than 64 bytes will be a runt frame. So it's basically like a piece, the broken piece, right? So this will be just usually discarded. So any frame that is less than 64 bytes is not going to be propagated, not going to be forwarded. And any frame that is more than 1500 bytes will be considered jumbo. So you can actually, within your own network, you can set your equipment to operate with jumbo frames, and there are reasons for that. It is more efficient, yeah, because every frame that you have, smaller frame, so there's this much data, and every frame will include this and that, which is not actually data. It's something, some control kind of, it's overhead. Yeah, it's something which is not data itself. So if you increase the size of the data, yeah, make this bigger, then a percentage of this in relation to the data itself will decrease, right? So if you increase the size of the frame, so but this is special cases. So those jumbo frames are not something which you they're not like runt frames. Runt frames are discarded because they're just considered to be not viable. Yeah, so they're not right. But jumbo frames there are some legitimate uses for jumbo frames, but you have to set up your network in the special way. We're not going that route. Yeah.
So the area about the jumbo frame or baby giant frame, is this what a company would do? Is this the area the company would go to kind of increase their mail limit sizes? Because you know that some companies don't receive mail over like 10 megs, they can set their limit to what they can receive.
No. It has nothing to do. So it doesn't matter. It doesn't matter what your mail size is, because your network communication will still be broken into frames. Yeah, it doesn't matter. So it's not related to the anything. So you're talking about application layer limitations. So this is all this attachment limitations will be application layer. It has nothing to do with that. So whatever size of your attachment is, it will be broken into segments, and then it will be it will become packets, and then they will become frames at some point, right? It doesn't matter what size, what your initial size of that attachment is. It's still going to be broken into segments, right? But the reason why would you use frame jumbo frames is, for instance, if you're a data center and there is a lot of lateral communication, so between the servers that are part of the data center. So every time you send a frame of this size, you send this much of data and that much of a junk, right? this much. But if you increase this to a bigger number, so this doesn't increase. You still use that much to send a single frame, but this goes much greater. So you send more useful data with the less of unneeded control information like this, right? So you increase your good put, yeah. So your useful data transmission of useful stuff will the efficiency of that will increase, right? Okay, so this is the reason why you would use jumbo frames, not because of nothing to do with email. Layer 2 doesn't care about if it is email or whatever it is. It doesn't matter. It doesn't matter to layer 2. It's not aware. Remember, the layers, they're separated from each other. Layer 2, all it cares about is what is the protocol above. Is it IP version 4 or IP version 6? And what is the technology below, physical one? Is it Wi-Fi? Or it has no clue if it is email or whatever. It doesn't look inside here, right? Data, the layer 2 will be not aware what is there. It is a black box, yeah, to layer 2. It doesn't care if it is email, web page, whatever you send, doesn't matter. Picture, video, whatever. Right. So coming back to the sizes, right? So these are kind of accepted standards, right? Let's not go into jumbo frames. I'm just saying that jumbo frames, there is a way of using them, but we're not looking into them. So for us, for now, for time being, we will accept that the frame should be between 64 and this, right? So this is these limits for this, for minimum and maximum size. So jumbo, yes, it can be used, but it has to be set up. So the devices that transmit these frames, they will not treat them as freaks, yeah. So they will understand, yes, this is a jumbo frame, and I know what to do. But it has to be set up first, configured. So if it is a large jumbo frame and device will not know what to do with it, it will drop that frame. Less than the minimum, greater than maximum, the receiving device will drop the frame because it won't know what to do with those. They are unexpected, basically, events. Yeah, so they're not going to be accepted. They will be considered invalid. Jumbo frames are usually supported by most fast Ethernet and gigabit internet switches and NICs. Yeah, but these are special cases. So 2 bytes type length. So what is a byte? Remember, 1 byte is 8 bits. This is 1 byte, yeah, 8 bits. Or, I mean, it doesn't have to be all ones, it could be zeros and ones, yes, so it could be anything like that. But it is a 1 byte. If you have 2 bytes, then you have 16 bits, yeah? You remember that. 6 bytes, so how many bits you've got? 6 times 8, you've got 48 bit here. 48 bit there. And this is the length of the MAC addresses. We will come to this later on. So you will see that MAC addresses are 48 bit long. Then the data frame, this is the frame check sequence, 4 bytes. So it's 4 times 8 is 32 bit. Yeah. And this is 8 bytes, preamble and SFD. Right. There is a Wireshark to examine Ethernet frames. It's a lab. Let's take a break, guys. Yeah, and we will do the lab afterwards. Shall we take? So 11:06. It's like 14 minutes until 20 past. Yeah, 20 until 20 past. Okay, break. Till 11:20. Yeah, 14 minutes. Okay, see you later. I will remove you from the class. Sahil? Hello?
Hello?
No, yeah, Sahil. I'm talking to Sahil. This is someone who is Sahil. Let me just write it on the screen. Maybe he can't hear me. I don't know. Let me just try. I hope you can see the message. Sahil? Yeah, Jeffrey, thanks for signing up. I'm going to put you in the class. Yeah, give me a minute. Okay, Jeffrey, you are in the class, so you should have access to NetAcad. So if you go to NetAcad, you will see your current. Go to dashboard and then you will see your class. It's called CCNA 1. Click on it and you will get access. Yeah, everyone. Also, new people. So who is it? Jeffrey and Jessica. Who else? Jamila. So you probably didn't include. You didn't install something which is called Wireshark. Yeah. So you need to do it now because we're going to use it in this in a lab. So you go to Wireshark. It's called wireshark.com. I'm going to put this into chat. Yeah, so it is. Yeah, you can do you can go. Yeah. If you're struggling, that's fine. So for those of you who haven't delivered, yeah, so see you next time. Uh, so for those of you who haven't installed Wireshark, you just go to wireshark.com and you click on download now, and you need to install this on your PC. So you can see that you can't really use a smartphone to access this class. Yeah, you have to have a laptop or desktop, whichever PC you're going to use. It is a necessity. You can't just get away with using tablet or smartphone. It's impossible. So not only because of Wireshark, then there is a packet tracer. So there are lots of apps that we're going to use, and they have to be installed on PC, not on smartphone. Right. So please install Wireshark, and when you do, you'll be ready to do the packet tracer, the lab. Yeah, not packet tracer, but lab. So new guys, right? New people. When you now, if you have an access to NetAcad, right? So this is how the course will look like on your computers, and so we are doing module number 7. right? So you click on it and it will take you to lab. Yeah, so it's under 7.1.6. There's a lab. You come, you click on it, and this is what we're going to do now. All right. So you, yeah, so you download. You can see this. I don't know, link. You can click on, and it will download the instructions how to do this lab. So this is it. And so we're going to do what? We're going to use Wireshark, that piece of software, and we're going to capture some frames which are going to be transmitted on your on your local link, and we're going to look at some of the structure of the frames, yeah, which will be captured. And so we're going to look at header fields in an Ethernet frame, and yeah. So okay, let's do this. Okay. Allow me to share my other screen because this one is not convenient for this purpose. Let me fire Wireshark first. So Wireshark, there you go.
Pavel?
So when you start Wireshark, this is how it's going to look like in the beginning, right? When you start it up, and you have to choose in Wireshark. If you have multiple interfaces, yeah. So on it could be logical, so virtual interfaces. They could be. Sorry, I'm just moving my microphone. It might produce some noise. So if you have multiple interfaces, you need to select which one is your physical one. So like going back to laptop, which has Wi-Fi and Ethernet, you might have both of them showing here. So in my case, it's easy. It is easy to see which one is being used because you will see a graph showing network traffic. Yeah. So here, in my case, it's called Ethernet. So I'm going to click on it, and if I double click, it will start capturing every frame that comes in and out of that interface. Yeah. So I will stop capturing. There is a button, red square, top left corner, and I just don't need to capture anything. Let me just read what's, let me show you. Yeah, so what the instructions for the lab. So we're going to use Wireshark to capture some frames, look at the structure of the frame, and that's it. Yeah. First, you need to find out what is your IP address and also IP address of your default gateway, of your home router. Right. If you are at home, that will be your home router. If you are not at home, it will be someone else's router. Your default gateway. So anyway, this is the command to use. So I'm going to fire command prompt, right? So I press Windows key on my keyboard and I start typing command prompt, top of the list, boom, press enter, and it pops up like this. So I need to type ipconfig /all. This is for Windows computers. If it is a Mac computer you're using, the procedure is different. And does it say here? Does it explain? I think we did it last time. So sorry. MAC. Yeah, IP config default gateway MAC. There you go. That's what you need to use. Okay, I'll put it in the chat. Sorry, I don't keep it in my memory for some reason. I'll put it in the chat. Andrea, you need to install it. So if you have a Windows, normal Windows, it will be 64-bit. So you need to choose Windows 64 installer, not ARM. ARM 64. ARM is a different kind of processor. So don't use it. It's probably not what you have. And don't use portable. Portable is, yeah, just install normal. Portable is something which you can take away with you. Right, so for Mac computers, you need to say netstart -nr pipe. Do you know how to do pipe? Pipe is the key on your keyboard, which is next to your left shift. It's backward slash. If you press shift and backward slash, it will give you pipe, right? So this is backward slash. If I use shift and backward slash, it will give me pipe like that. Yeah, it's called pipe. Okay, but
So Pavel.
Yeah.
So Pavel, sorry. I've got a bit lost. What I've got my IP address and gateway. And you was talking. I wasn't actually listening. But what's the next stage we have to do after that? Was it something in packet tracer you wanted us to do? I've launched packet tracer. I mean packet tracer. Wireshark. Sorry, I launched Wireshark.
So far, we haven't done anything. We just want to establish what is your IP address and IP address of your default gateway.
Okay, I got that.
That's all. So for that, you need to type ipconfig /all and press enter.
Yeah,
So Jimmy, grep will not be understood by Windows. Windows don't understand grep. Grep is Linux Mac command. So ipconfig /all, press enter, and note down your IP address and your default gateway IP address. So my IP address is, where is it? Yeah, here. So this is something, this is my setup. Yeah. So this is what I want, IP version 4 address, and you can write it down if you can't remember it. And you need default gateway as well. Okay. And you can see there is a physical address, which is a MAC address, but we'll come to this. Okay, so after executing this command, we can come to the next step. Let's go back to the instructions. Instructions are here, right? So instructions tell us, so this bit is done, step 2. We need to come to step 3, examine Ethernet frames in a Wireshark capture. The screenshots of the Wireshark capture below shows the packets generated by a ping being issued from a PC host to its default gateway. So that's what we need to do, right? So you know your default gateway now, and you start Wireshark capture, right? So you need to go to Wireshark. Sorry, where's my Wireshark? There you go. This is my Wireshark. Yep. And I need to begin capturing now, right? So I stopped it before, so by using this red square. So I need to start new capture by clicking blue fin, yeah, Wireshark, because it's a shark, so it has a fin. Blue fin, right? So click on it. It will ask, do I need to save the previous capture? No, I don't. There's no need to. There's no use for it. So I will just say continue without saving. And now I'm capturing everything that is going in and out from my network card, right? But I don't want any of that. I need to filter. So up in the Wireshark, there is a field where I can click and it says apply a display filter. So my filter will be ICMP. Yeah, ICMP. Please write it down. This is the protocol which we're going to look for, right? So we're going to filter for only for ICMP transmissions, right? And there are none because there is nothing to display because there are no ICMP packets, right? So we need to generate some ICMP traffic. And to generate, we need to send a ping. So ping, when you send it, it will, remember, it will send 4 messages to the destination, and it will wait for 4 messages to come back, 4 echo requests, echo replies. So 8 altogether you expect to capture. For Wireshark to capture, and ping is an ICMP is using ICMP protocol. ICMP is the name of the protocol which ping utility is using, right? So we leave Wireshark to capture to filter on to display only ICMP messages, and now we need to go back to command prompt, which is here, where we typed ipconfig or whatever. If it is if you're using Mac computer, it will be your terminal. Yeah, so it doesn't. It's not called command prompt. But anyway, so here you need to ping your default gateway. Remember the address? I hope you wrote it down. So 192.168 is mine. .1.1. This is my home router's IP address. Okay, I'm going to send a ping to there and hopefully receive 4 replies, 4 echoes, echo replies. So there you go. 4 went out, 4 came back, and I can go now to my Wireshark and I can see these 8 messages. Yeah, 8 out, 4 out, 4 back, 8 altogether. So do I need to continue capture? I think I probably need to stop. Let's go back to instructions. What does it say? Do I need to stop? Actually, it doesn't do much. Actually, it needs, this is just a screenshot, actually. Oops, sorry. I think I probably went too far. So ARP is a communication protocol that is used. So this displays is pre capture that was done somewhere, not locally. So it displays broadcast ARP. It's ARP protocol. Yeah, so you can see it. So okay, what we can do, okay, to do this, I can go back to my Wireshark. Where is my Wireshark? Here, and instead of ICMP, I can also say ICMP or so ARP and or ICMP. Okay, so I'm going to filter for 2 kinds of protocols. Oh, there are so many ARPs. You can see there are so many ARPs. And only 8 ICMP messages. All right, so going back to our instructions. So what do we need to do? Right. If this screenshot highlights the frame details for an ARP request. All right. This screenshot highlights the frame details for an ARP reply. Right. Good. And so examine the Ethernet 2 header contents of an ARP request. The following table takes the first frame in the Wireshark capture and displays the data in the Ethernet 2 header fields. Preamble not shown in the capture, destination address, broadcast, source address. That is where it comes from, source, and broadcast. So broadcast, you can see what it looks like, all Fs. And remember what F is, hexadecimal F, it's 4 ones, yeah? So if you translate it back into binary, you will understand that it broadcast means all ones. Yeah, 1 1 1 1 1 1 32 ones. Sorry, not 32, 48 ones. Yeah. Do you remember that? Yeah, from our someone shared ipconfig. Most common terminal commands. Right. Okay. Anyway, remember F from hexadecimal F? It is 4 ones. Yeah, from last session. So if you can see how many Fs, 12 Fs. Yeah, pair of Fs. It actually means 8 ones. Yeah, binary 8 bits, all ones. So if you have 6 pairs of Fs, that is times 6. So you've got 8 times 6. So you've got 48 ones, right? So this shows you the broadcast address, right? So broadcast is something which is it is a layer 2 address for the frame. Each address is 48 bits long or 6 octets. So 6 octets, yeah. So 1 octet, 2 octets, 3 octet, 4 octet, 5 and 6 octets. And each octet is separated by a colon. So 2 Fs is a 1 octet. Yeah, each F, each hexadecimal is 4 bits. A pair of hexadecimals give you 8 bits. So it's an octet or byte. Yeah, so you can call it octet or byte. And it's just to demonstrate how it looks in a capture, so you can kind of visualize it. Yeah, and you can relate to it, right? So there's nothing fancy in this lab. It's just have a capture, have a look at it, and just go through the fields, through the different layers, and just understand this, how the MAC address will look like. So here, source address gives you del, and then it gives you 6 hexadecimals. Or in brackets, it will display the full 12 hexadecimals. Yeah, so 48 bits, 12 hexadecimals. Why does it say del? Because the first half of your MAC address will identify the manufacturer, right? So you can see in mine, where's mine? Capture, there you go. So you can see del source, and you can the del source can I increase the size? Sorry. Give me a sec. Font. Yeah, font. I'm going to increase it to, let's say, 20. How about this? Will it work? I need to apply. Ooh, maybe too much. Give me a second. 16.
Yeah, that's good.
Yeah.
Yeah.
Okay.
The
Yeah,
TP link. What? That's your modem router.
My router. Yeah.
Router.
Yeah. So
Okay.
basically, yeah, it has yeah. So my Dell computer is communicating with my router. Yeah, which is TP-Link, and it is easily identified because each network interface card, when it is produced, first half of it, first 6 hexadecimals, first 24 bits will be identifier of the manufacturer. So if I'm Dell, I'm going to assign this MAC addresses at the time of production. So I'm going to do them in hundreds, thousands, millions, whatever. Yeah, depending on how large is the company, and I will produce them one after the other, and I will give the assign individual MAC addresses, but the first half is will be used to identify myself, a manufacturer, and the second half will be assigned will assign unique addresses, right? So unique addresses. You can trace routes to google.co.uk, no problem. Yes, Jimmy. Yeah, you can. So, and now I've got, what is this? Vantiva Tech, I don't know what that is, on my network. What is it? Is it ARP? Oh, it's someone is asking, okay, it's some other device is asking who has, all right, so 1.9 is I've got another router here which I use as an access point. So it's basically it's another router I've got, and it's identified as Vantiva. I didn't even know it is a Vodafone router. I reuse. It's my old Vodafone router, but it is identified here as Vantiva Techn. So I guess it's sorry.
Why is there so many lists there if you're not sending or receiving anything?
Yeah, ARPs ARPs will be, well, first of all, I'm sending a lot. Yeah, so if I remove this, remember I haven't stopped my capture. So if I remove the filter,
Yeah.
it will show. So why doesn't it work? I press enter. There you go. So the capture is still going. So I am receiving a lot. First of all, we've got this Teams meeting, so most of it will be Teams. Yeah, here.
Oh, yeah,
Most
of
of the
course,
traffic.
of course. Yeah. Okay.
But apart from the traffic that happens like ongoing, there are some like ARP or ICMP, if I press enter. So now I'm applying a filter. I only want to look at ARP or ICMP messages. Yeah, so I don't need anything else. So ARPs, it is something which is done automatically if there is some address resolution. It's called address resolution protocol. If it can't, if it doesn't know the IP address, some MAC address of an IP, and then it will have to resolve it. And this is what ARP is for. We are not looking into that, guys. Okay, let's not go there. There is a whole module dedicated to ARP messages. Yeah, it's a kind of it's not complex, but it is important part of this communication. So ARP, what it does. At the moment, we look at simple stuff. We just look at the capture, and we need to understand that where the source is and where is the destination, right? So first ARP was sent from my computer to TP-Link, and then there was a broadcast. So this is another ARP message. So this computer, sorry, not computer, but this device was looking for an ARP reply, and that's why it was called it was sent as a broadcast. So broadcast means it goes to everywhere, all the devices on the same link, and then it was repeated a few times. So first for one device, for another device. It doesn't matter. It doesn't matter why ARPs are sent. What does matter here is that we are looking at some communication locally between my device and other devices on my link. Yours will look different. Yeah, so your captures will all look different. But the idea is that we look at frames, at layer 2 frames, which you can, so here below, right? So you can expand the Ethernet 2 layer. Let me just, sorry, I think it's still a little bit too big to my liking. Let me just adjust the font. It's 16. Let me make it 14. I think I will like it more. There you go. I hope it's still visible. So there you go. And that's all we do, right? So it's I believe this is the nature of this Wireshark lab. Okay, so it tells you the source address, which we looked at, right? So the source address, like ping, where are my pings? Here. So the ping, if I look at the bottom, are Ethernet layer, right? I'll highlight Ethernet layer, and you can see my destination is TP-Link. So this is my local router, and my source is my computer, Dell, right? So it has this MAC address, and type is IP version 4. And you can see in brackets that this is the identifier, hex identifier of IP version 4. IP version 4 protocol is being used. So this is the IP addresses of 1.8 is my computer, 1.1 is my default gateway, my router. And this is the actual protocol being used. So this is an echo, that ping, right? So it's an echo ping request. Okay. The data itself is 32 bytes, and you could see that the data is 32 bytes. If you go to command prompt, where you send your pings first, yeah, pings. Remember the pings we sent, and you can see that here byte the size of the ping, the message that I sent from my computer to the default gateway is 32 bytes, and we can also see this in Wireshark, right? The size of that message. Blah blah blah. This is the data itself. In hexadecimals, and this is 32 bytes. And then I sent one from my computer to the default gateway, to the router, and then I received the reply from my router, from my default gateway, back to my computer. So now I'm looking at the reply. I highlighted it, and I'm looking at Internet Control Message Protocol. Now it is a reply. So before it was a request, first coming from my computer to the router. Now a reply comes back, and I'm clicking on it, and I can see it is a reply. It does say here, echo ping reply, right? Still 32 bytes. And but we would like to look at Ethernet layer, at layer 2, right? So here I'm expanding Ethernet, and you can see now. So initial ping coming from my computer to the default gateway, source is Dell, destination is TP-Link. I'm looking at reply, clicking on reply. Now the source is TP-Link, my router, and destination is my computer. So because it goes in opposite direction, right? And I think that's it. So distance, IP version 4, yeah. I think it's, we looked at it. So in preferences, if you click on and you can choose your layout, yeah, and you can select, you have different variations. You can play. So the default is 1, 2, 3. So one, like mine, one, second is the default option, but you can change it according to your preferences. Well, you click on the capture, and it will appear at the bottom. Like what? It depends on which layer you click. So there are you can expand different layers. Don't double click. Don't double click. Just expand. Yeah, expand. Yeah. Okay. Good. So again, there is nothing fancy about it. It's just So the purpose of this is just for you to get used to Wireshark and just have a look at layer 2 information like MAC addresses and so on. So you get used to this kind of stuff. Yeah. Don't expect it to, there is no catch here, right? There is nothing really difficult. So type of frame, yeah. So you can see there is IP version 4 protocol. This if you look at the message, the type if it is IP version 4, it will be identified in hexadecimals as 0800. Yeah, and if it is ARP, then it will have a different identifier. So here, where's the so ping? I look at ping and type IP version 4. Can you see highlight? If I click on ARP, it will be identified as ARP protocol, right? So above layer 3 protocol in ARP is a separate kind of protocol to IP version 4. So IP version 4, IP version 4. If I click on ARP message, it will show type ARP in brackets 0 cross or X 0806. Yeah. Right. What else? Sorry. Yeah. Frame check sequence. The trailer of the frame will not be shown. So this error correction sequence. Yeah, it's not going to be there. It's not captured. What is the significant about the contents of the destination address field is a MAC address, so where it goes. Why does PC send out a broadcast ARP prior to sending the first ping request? Well, they don't. Okay, so they don't explain what ARP is. So basically, okay, ARP. I'll show you. I'll show you. Where's my paint? Paint. So what ARP does? Yeah, why do we need ARP? Quickly. New. So my device, my computer, wants to send a ping to here, to my router, right? I am at 192.168.1.8, and my computer will know how to find default gateway. If it doesn't, it's a problem, right? So every device needs to know how to find default gateway. Otherwise, my PC won't be able to communicate with any other networks. Yeah, because any other network needs to my device needs to communicate with. The communication will happen through that default gateway, right? Default gateway is the one that passes through all the communication to other networks will pass through. That's why it's called default gateway, because it is default and it is a gateway, right? And so this information is known. This IP address of my router, of my default gateway, is known to my PC, right? My PC also knows its MAC address. It is available. What is the MAC address of my router? Yeah, a router will know, but so this is the MAC address of the source when the ping is being sent, and this is MAC address of destination. My PC doesn't know this. Yeah, it knows the IP address of the router, but it doesn't know MAC address of the router. So to find it out, so it needs to send it here, right? It needs to send it here. But it doesn't know MAC address, but it does know the IP address. So what ARP does, my PC will send a broadcast message. It will say it is an ARP message. It will go to everywhere, to every device available on that network, on my network. Yeah, here, every device. So if I have only 2 devices or multiple devices, it doesn't matter. All devices will be addressed. It is a broadcast message, goes everywhere. So ARP is the ARP message to find out MAC address of my router will be a broadcast. It will say, my device will send ARP message saying, who's got this IP address? Please send me your MAC address. All right. And my router will receive this broadcast and it will say, oh, this is my IP address. I need to reply. And my router will send back an ARP reply back to my PC with this MAC address. When my PC receives it, and MAC address of destination will be known, and that's when the ping will be ready to be sent to the router, right? So unless my PC, my device knows MAC address of the destination of the router, unless it is already known, it has to send an ARP request. So if it does know, if it is in my ARP cache, so locally my PC might already. So if my PC communicated with my default gateway, which normally happens anyway, so continuously, so this MAC address of the router will be here in my MAC address of destination of my default gateway, will be stored in my local ARP cache, right? But if it is the first communication or after a long period of inactivity, that cache will drop that MAC address of my router. Right? It will be deleted from the memory of my device, and ARP request will have to be sent again. So ARP is a way of finding out what is the MAC address or which is associated with the IP address where the message needs to go, right? So ping, yeah, ping. I say ping 192.168.1.1. What is the MAC address which is associated with this ping? My PC doesn't know. It will send before, so ping will be held. Yeah, it won't be sent, so it will be put on hold, and ARP will be sent first. Who's got this 192.168.1.1? Please send me your MAC address. So my router will reply. My computer, my device, my network interface card of my device will not network interface card, but my computer, my device will know the MAC address of the destination after receiving ARP reply, and then ping will be sent to the destination, to my default gateway. And by the way, this is the reason why there are 4 pings. Yeah, remember we sent 4 pings. Ping 1, yeah, then you said ping another one ping. So if you go to command prompt, you will see there are 4 pings. And this is exactly the reason why the first or second ping, sometimes even 2, first and the second, sometimes are not successful, because of that the MAC address of the destination needs to be found out. Okay, that's why the sometimes the first ping is not successful, because it will take a bit of time for the ARP to be sent, broadcasted, and then it will wait for reply. While it is waiting, there is a timeout
It's
for.
just going to be harder because it's at the end.
Sorry, I think it's. So yeah, we're going to talk about ARP in detail later on. Okay, so there is a whole module talking about this, but for now, it's just this is the idea, right? So ARP, if MAC address of this destination is not known, but IP address is known, because the ping will be sent to the IP address, not MAC address. Yeah, so a MAC address of the destination needs to be found out. That's the nature of thing. Yeah. 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 Yeah, absolutely. Yeah. Yeah. Okay. Yeah, so whoever has got this IP address, please reply and send a MAC address, which is associated with that IP address. So what else we need to do? I think why is the vendor ID or UI of the source NIC is in the ARP reply. So ARP will include the vendor OUI is a vendor ID, organizational unique identifier. So it will say if it is TP-Link or Dell. So this is why, yeah, because it is. It isn't. So when it comes from ARP reply, it will include the MAC address. So vendor ID will be there, right? Because it's part of the MAC address. So what portion of the MAC address is the OUI? First half. So the entire MAC address is 48 bits. So 24 bits or 3 octets, 3 bytes. Yeah, so 48 bits is 6 bytes. Yeah, 48 bits, 6 bytes. 6 times 8, 48. So first 24 bits or 3 bytes will be first half will be used to identify the manufacturer. And the second half will be unique identifier given to each individual network interface card. What is the NIC serial number of the source? Yeah, well, you can have a look. Yeah, so what is the NIC serial number of the source? So we've done this. Okay, start capturing. So we've done all of that. Yeah, filter ICMP from the command prompt from Windows ping the default gateway. Examine the first echo, first ping request, then the second ping, and this explains everything. You can click the greater than sign at the beginning of the second line to obtain more information about the. So this is expanding this. Yeah. So click and expand. Right. We've done it all. What time of frame is displayed? So you can have a look. What is the source IP address? You can. It's all there. And packet bytes. You can click any line in the middle section of the highlight to highlight that part of the frame, hex and RC, and in the PTT, click the internet TTT, then what do the last highlight, last two. You can click sorry, in the middle section to highlight that part of the frame. We need to click, okay, internet control. So we need to click on the ping, sorry, ping and middle and internet control. Yeah, and echo request. So ICMP, Internet Control Message Protocol. Yes. So what do we need to do? Let me just read it again. I don't know. My mind can't understand what they want. You can click any line in the middle section. Yes, to highlight that part of the frame. All right. That's what we did. In the packet bytes pane. What is the packet bytes? On the right. Yeah. Bottom right. Click the internet section in the middle section and examine what is highlighted in the packet bytes pane. What do the last two highlighted octets spell? So I think, so basically when you click here, you can see on the left, it highlights what it actually means. So this is the entire frame. Yeah, on the right, it tells you the entire frame from the beginning to the end. And when you click on the left, different parts of that frame. So checksum will be here, 4D53. That is hexadecimal. When you click on something here, so you can see identifier 0001 on the left. On the right, it shows you 0001. All right. Basically, it's just on the right here, it's kind of raw data. This is just hexadecimals. Yeah, it's hexadecimal numbers. And on the left, it tells you what it actually is and what actually it means, because it just follows the structure of the frame. Yeah, so frame comes like that on the right. Yeah, 30. Well, it's not 30. 306893A05792 and so on. So it's a sequence. But because we know the structure of the frame on the left, we know what each, and because of the position those numbers are at, so we know we can understand what it means. So that sequence of hexadecimals, actually it's bits, isn't it? But we just represent those bits in hexadecimals. Remember? Yeah. So hexadecimals is a way we agreed to represent bits. Remember, the actual transmission will be zeros and ones. But to shorten that long sequence, we just in the right hand side, on the bottom side, half right hand side, we represent those bits as hexadecimals. Each hexadecimal is 4 bits. Yeah, you remember that from last session. So each of those numbers is actually 4 bits. Yeah, so 5 means something in bits. Yes, so it's 1001. That is a 0101. Yeah, that is the 5 in binary, right? And so on. So 0 is just 4 zeros, 40 in binary, and so on. 1 is 0001 in binary. But each hexadecimal is 4 bits, and that's what it asks you to understand here. Sorry. All right. Yeah. So instructions are right here. What do the last 2 highlighted octets spell? What highlighted octets? What highlighted octets? I don't know. But the principle you understand. Yeah. I don't. I can't make out what they want from this question, but the principle you understand, right? It doesn't matter what this means, because it's just some gibberish. Click the next frame, and maybe I don't know.
Hello, sorry, Pavel.
Yeah.
Just raised my hand. I don't know if you can answer for me. I don't know how to have a log in the practical lab so I could do the things, but yeah.
What practical labs? On Cisco.
Yes.
You need to go to NetAcad, log in with this. You registered today, haven't you? So you need to use
Yes,
that.
I did, but I don't know how to do it. I'm just asking you. So how can we do it? Because it's my first day. So you just explaining. I'm just lost, you know.
Yeah, so I did ask you to download a Wireshark. So Wireshark, this is what you need. Yeah, you go to wireshark.org and you need to download it. Yeah, so I'll put it in the chat if you want, and you download. This is the app we're using.
Yes, that's what I'm looking for. And then what should I do next? It's log in the same.
No, you don't need to log in. Wireshark, it has nothing to do with NetAcad. It's a separate application. You just install it on your computer.
Right. That's it, yeah?
Yeah.
Okay, thank you.
Right. So before we send ping to default gateway, right? And now, as in previous lab, remember we did it with the first lab in Wireshark. Then we can send ping to remote destination, like ping cisco.com. And if you do this, so in Wireshark, you will be, so if you have a local PC, your PC here, and this is your router, right? And then it goes blah, 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 and it reaches cisco.com, right? This is some sort of a server somewhere. It will reply to you, right? Cisco.com. You ping to cisco.com. And so first we pinged default gateway, right? Default gateway. Ping, we said, in my case, it was 192.168.1.1, right? So ping went here and then it came back. Now we send ping to cisco.com and it will come back from cisco.com, right? So, and if we do this, so I will, what I'm going to do, I will remove ARP. I'll just leave my pings. I will stop capturing. Yeah, I forgot. So you can see I've captured 8 ICMP messages, 4 pings, 4 replies. Yeah, 4 requests, 4 replies, 8. And if I look at Ethernet, so below, yeah, I can expand and I can extend this. I can expand this section and it will show me where, which MAC addresses were communicating when I send a ping to my default gateway, to my local router. So it was MAC address of my PC and MAC address of my router, right? I can, what I'm going to do, I'm going to take a screenshot of this so we can save it and then compare it. Sorry. So I will keep it open. I'm not going to delete anything. So now I will stop my, well, I have stopped my capture anyway. So this was ping going to my default gateway, to my local router within my, yeah, so my home router. Now I'm going to start capturing again, continue without saving. And I'm still capturing only ICMP, but this is a new capture, right? It's going on. So if I remove the filter, press enter, so you can see there is lots of packets being sent in and out. Yeah, but if I filter ICMP, press enter, nothing is displayed because I'm filtering only ICMP, and there is no ICMP traffic at this point. What I need to do, I need to go to my command prompt, and I need to ping cisco.com. So 4 pings will be sent, 4 pings will come back, right? So I can stop capturing, and now I can see there are 8 again, right? 4 went out, 4 came back. Same story, but now the destination IP addresses are different, isn't it? So before, I'll show you, that's how it looked like. This was my previous capture. So the IP addresses were local, yeah, destination and source. My PC went to my local router. Now the destination IP is Cisco. It's outside, remote network. But if you look at Ethernet frame here, MAC addresses remain the same. Yep. And if I look here again, you can see the MAC addresses. They are the same, right? So destination and source, my PC, and yeah. So Dell is my computer, TP-Link is my router, right? Here, the same story. Dell is my computer, TP-Link is my router. It's just to demonstrate that MAC addresses will be still used, local ones, yeah, between my computer and my router, regardless what is the final destination. So first ping was sent to my local router. The second time, the ping was sent to Cisco, but MAC addresses don't change. The IP address do change IP addresses, but MAC addresses don't. And this is the whole point, all right? just to demonstrate exactly this to you, which we kind of looked at last time, to be honest. Okay, so we're repeating this. Okay, repetition is what? In Russian, there is a saying, repetition is a mother of learning. I don't know how it translates. In English, there is a saying, practice makes better or something. What is the English saying? Makes perfect. Yeah, something like this. Yeah, makes perfect. Yeah, so yeah, repetition is mother of learning. Sort of. That's the direct translation from Russian, but exactly the same meaning. Anyway, yeah, so my mother tongue is Russian. If you wondered where my accent comes from, I'm from Central Asia, but yeah, ethnically I'm Russian. My first language is Russian. Examine the new data in the packet list pane. So anyway, so you can do do these reflection questions. Okay, so source, destination, compare IP addresses, compare MAC addresses, and source destination capture. Put them on the list and do your comparison if you need to. Right. So basically, compare what I've just done. Compare this with that. Yeah.
Pavel,
Yeah.
this it doesn't capture. Is there any way I can see the public IP address in the Wireshark or no? Just wondering, just curious. That's all. Otherwise, it's fine.
What can you do? You can probably let me see. Let me just close
I thought
this
you
down.
have done it something. It's okay if
No, I think it's well.
it's possible.
I think trace route should do it. So if you start your capture and but then you need, yeah, I mean, it's just a whole different story. Let's not dwell on it. But you
Okay.
can. It depends on what protocol you're going to use. Yeah. So I think it's if you still remain okay. Continue without saving. Okay. Let's try and see if I can trace route something. Will it display anything? So. No, it still doesn't do it. No, trace route. Yeah. No.
Okay, no, don't worry, it's fine.
I think there should be. Yeah, not from the top of my head. I don't remember. Maybe probably there's a way to do it. Yeah, it's not a difficult one, but I don't know. There's still a message to Sahil. Where's Sahil? Sahil is not with us. Anyways, that's good. Well, it's not good, but it is what it is. So we are, yeah, okay. We've got something. We still have time. Okay, guys. I spent quite a bit of time, to be honest, on this Wireshark, which is it's not that important, but it is important. It is important as an introduction to Wireshark and the structure of the frame and the meaning of this. So how MAC addresses are being used locally on the local link, regardless of what the destination IP address is. Yeah. So this is the whole idea. And also, I hope you remembered a little bit about ARP. You don't need to, but I still don't understand why Cisco sometimes asks these questions like, what is ARP? Why does it do it? Without ever mentioning ARP before. Right? It's a bit weird, but it is. Well, this is the way it is. So Cisco likes to introduce some concepts, but bit by bit. So they give you a little bit, and then later on they will come back to the same topic, but give you more in-depth explanation. And they might revisit it again later on with again going a little bit deeper. So just get used to it. This is the way the materials are structured, and so this is the way it's all delivered. So it does work. Yeah, so it's a proven method. It's been in place for many years, and it does work. So just stick with it. So if there are some things we don't understand, you're welcome to ask. But if there are so like ARP, as I said, there's a whole module we're going to talk about this neighbor discovery. And okay, Sahil didn't read the message. So let's talk about Ethernet MAC address. We kind of looked at it anyway. And I wish that lab was a little bit, well, after this introduction, but maybe it will help you understand better now what is a MAC address. Okay, so MAC address is a 48 binary value, so zeros and ones. Yeah? And because it's quite a large number, we agreed for us, for human's sake, to use hexadecimals to represent it, because 48 zeros and ones is impossible for us to remember, right? But at least with this, with hexadecimals, 12 hexadecimals, it's a bit easier. And remember, each hexadecimal is 4-bit number. So F, yeah, is for in binary. You can represent as all ones, and so on. So A is looks like this in binary. Yeah. So for those of you who missed last session, we did conversions. You have to do it yourselves, unfortunately. I mean, you missed quite a bit. So, oh, sorry, I need to switch my screens. There you go. That's better, isn't it? So yeah, so 48-bit can be a long 48-bit long number, binary number, can be represented by 12 hexadecimals. 12 hexadecimals are 16 symbols we use to represent any number. Like binary, in binary we use only 2 symbols, zeros and ones. In hexadecimals we use 16, 0 to 9 plus A, B, C, D, E, F. So 16 altogether. Right. Given that 8 bits or 1 byte, or we sometimes call it an octet when it comes to IP. Octet means same thing as a byte, isn't it? Is a common binary grouping. So binary 8 zeros to 8 ones can be represented in hexadecimal as the range 00 to FF. Yeah. So 8. So you take first 4, and this will be hexadecimal 0, and you can have second 4. This will be hexadecimal 0 again. So instead of using 8 zeros in binary, you can represent it by 2 hexadecimal symbols. You shorten the numbers. Yeah. So so visually it's easier for us, for humans. And for 8 ones, or like so, you can represent in hexadecimals as F. Yeah, you don't need to help me. It's my Alexa replying to me. So F is 4 ones. Yeah. So 8 ones, you can have F and F. Right. When using hexadecimals, leading zeros are always displayed to complete the 8-bit representation. Yes. So because if you have hexadecimal 00 and you drop this, this becomes ambiguous, right? So if you have MAC address which looks like this, whatever, yeah. If you drop leading zeros, like if you don't display and you start with 1, it becomes like it's not it's basically it's not allowed. Yeah, you don't drop the leading zeros here. Yeah, so these 4 zeros will be displayed. No, sorry, not here. Here, yeah, this leading 0 will be displayed still. hexadecimal numbers are often displayed by value preceded by 0 times and like x. Yeah, so this, when you see this number, it is a hexadecimal. It's not it's not a decimal number. So if there's nothing in front, it's a normal 73. But if you see this is hexadecimal, and remember what it means. It means 7 times 16, right? Plus 3. So this is totally different numbers. So 70, 76, 112. So this is decimal 115, isn't it? If you translate. Well, unless I made a mistake, probably not. Also, you can say, sometimes it is represented like this: 73 and capital H. That will show you that it is a hexadecimal number. So when you see this, remember it's not a decimal; it's a hexadecimal. So Ethernet MAC address. So it's a 48 long number. First 24 will identify organization, manufacturer. It's called OUI, organizationally unique identifier. And the second half will be vendor, the manufacturer will assign in sequence. They will keep this list, and they will just as they produce network interface cards, they will assign them one after the other, right? OUIs, it doesn't mean that one organization will be identified by one OUI, because if it is a large organization, it will produce enough to, so it won't, one OUI won't be enough. So they will use multiple OUIs. So you can have, if it is a HP, and this is a huge corporation, they produce lots of this, lots of interfaces, cards. So they will have multiple OUIs, but each. So if you see a MAC address, there is a service you can Google who is the manufacturer. So if you go to can Google OUI MAC address lookup. Yeah. So there you go. So Wireshark has it, or there are other. So you can go to Wireshark, and basically, what you can do, you can just type your MAC address of some interface card, and then it will tell you who is the manufacturer, because they will know who made what. Yeah, so they will keep track of those OUIs for it's not a secret. Right? All MAC addresses must be unique to the Ethernet device or Ethernet interface. Yeah, so there are no identical MAC addresses in the world, even though saying this, they can be spoofed. Yeah, it's not how they're supposed to be, but yeah, so it is easy to spoof. So you can have a software, and it can change your MAC address. So all vendors that sell Ethernet devices must register with IEEE. Again, can you see that IEEE? What a powerful, influential organization it is. To obtain a unique 6 hexadecimal 24-bit or 3-byte code called the organizationally unique identifier, OUI. So
the ID. তাহলে তুমি কি রেডি আছো?
Right. Frame processing. Okay, let's talk about interesting stuff.
Pavel,
Yeah.
sorry, can I ask a quick question? Just back regarding the MAC address, you said that they can be spoofed, right?
Yeah.
So when that happens, that means that basically both you and the person spoofing your MAC address will get your information, right?
It will be doing what, sorry?
Does that mean that both yourself as the source, so you got the MAC address, the MAC address is on your NIC device, yeah, and
Yeah.
then someone has spoofed your MAC address, that means they will get the same information that you get coming to your MAC address, correct?
Yes, this is the danger. So someone can spoof your MAC address and basically direct communications meant to you to reach you. They will receive that communication, and this is one of the sort of these network attacks that can be done. Yes.
But you still get the information as well, though, right? Because you still got the same MAC address, or does it stop it coming to you?
No.
Live.
Well, if it is a switch. So we'll come to this. So the switch will direct the messages to you or to another one. So it depends. So if they can spoof and they can convince the switch that they are the right owners of that MAC address, so the switch will ignore you and they will. But it depends. Okay, so it's the switch will know where to send it, right? So usually it's the switch that makes this decision. So frame processing. When a device is forwarding a message to an Ethernet network, the Ethernet header include source MAC address and destination MAC address. Yeah, so the header frame will and destination will always come first. Source will come next. And and the reason is because when the frame is being transmitted, yeah, and comes into the switch, so it is important to place the destination up front so it can be read immediately first before the source, because this is important. Yeah, so you place source first because where it comes from is secondary. Where it needs to go is the most important. So because this will allow the switch to forward it as soon as possible. Yeah. Well, if this is so the switch there are different methods of forwarding frames, and if switch is set to this kind of forwarding method, when it will be enough for the switch to read the destination and it will start forwarding immediately. This we'll look into a little bit later. So now in this module. So when NIC is receives Ethernet frame, it examines the destination MAC address to see if it matches the physical MAC address that is stored in RAM. Right, so I'm the device. I'm receiving a frame. I need to see if it is meant to for me. So I check if the MAC address, destination MAC address, is mine. If it matches, yes, I will process it. If it's not mine, if it's not meant to reach me, I will just drop it. And so processing a frame means that I will accept it. I will start de-encapsulation. I will pass it through all these layers of OSI layers up to IP, then to transport layer, and then eventually to the application. Ethernet and NICs will also accept frames if the destination MAC address is broadcast. Remember, we saw the ARP messages. They had this FF broadcasts, broadcast addresses, and which so ARP will send so 12 Fs. Yeah, so ARP when it doesn't know what is the MAC address of the given IP address, it will send a broadcast, and broadcast is all Fs. Well, not all Fs, it's actually all ones. Remember, 48 ones. Yeah, and these messages are usually processed by all NICs. Every NIC will receive it and it will check, because broadcast means that it is actually for you, for everyone. Yeah. So any device that is the source or destination of an Ethernet frame will have an Ethernet NIC and therefore a MAC address. Yeah? By the way, MAC address, your Bluetooth will have a MAC address as well, and not just Ethernet. So Wi-Fi will have a MAC address and so on. This includes workstations, servers, printers, mobile devices, and routers. Yeah? So if you have a smartphone, you can have a look at the settings and you will see multiple MAC addresses for Bluetooth, for Wi-Fi. It's just something you can relate to, right? Not only computers will have MAC addresses. So unicast MAC address, right? Unicast MAC address. So this is the source. This is the source, and I need to send a frame to the server. This is the server, and this will be a unicast message. So I need to send it. So destination is this, isn't it? And the source is this, right? So this is the destination. So this is unicast. I need to, well, the communication will happen to the server's IP address, yeah? So IP address first, and then if this H1 computer, H1, if it hasn't, it needs to send something to the server, which it knows the IP address of, but it might not know the MAC address. So to be able to input the MAC address, destination MAC address into the frame, it needs to send ARP first. So it sends ARP. ARP message will be broadcast, and the ARP message will say, whoever has got IP address such and such, please send me MAC address. And all these devices will receive this broadcast, and only the server will say, yes, this is my IP address, and I have to reply with my MAC address, and it will send an ARP reply back to source host. And that host will receive this ARP, and then it will be ready to send a frame to the server. Before it establishes the MAC address of the server, it can't directly communicate with the server. It has to send this ARP broadcast. But after it receives a reply from the server with the MAC address, it will put it into the frame here, and it will send messages directly to the server. This will be unicast, not broadcast. Uni means to the single address, yeah, not broadcast. So, what? Sorry, are you okay?
That
What?
I put some of the wash, I have to put the rest, but I feel it that go in.
Sorry, who is it?
Mum.
Oh, Frank. Sorry, Frank. I think it's you. It's not. Yeah, we can hear your conversation. It's not a problem. So the frame, basically, yeah, frame. It can be unicast, sent to just one server. Yeah, so here, or it could be broadcast like ARP. But source will always be unicast. Yeah, so the source of the message cannot come from multiple devices. It has to originate in one device only. Multiple devices cannot be the authors of the same message, the sources of the same message. All right. So ARP is something we use for IP version 4, and for IP version 6, we use similar protocol, similar method to find out the MAC address of the final destination. Not final destination, but it's not the final destination, but the MAC address of the device where it needs to go, right? And it's in IP version 4, it's called neighbor discovery. So it's like almost identical to IP version 4 ARP. But it works in for IP version 6. Yeah, remember those 128-bit long new kind of IP addresses. Source MAC address is always unicast. So broadcast, yeah. So now we've got another. So I need to broadcast a message to multiple destination, to not multiple but all. Yeah. So this is a broadcast. Every device will receive it. So if this is the case, so the destination MAC address will look like this: FFFFFFF, which means basically just once. Yeah. Yeah. If you translate it, that 48 ones, 48 of those. So this will be 48-bit. So 48 of those, yeah. It is flooded out all Ethernet. So when the switch receives a broadcast, it will send it out of all ports available, yeah, except the incoming port. Obviously, there's no need to send it back to where it comes from. It is not forwarded by a router. This is important. This will be reiterated later on. So if you have a so this is your network, right? Subnet. All the devices on the subnet will receive this broadcast. But if you have a router, this is your default gateway, right? So locally, broadcast will be broadcast. But when it comes to your router, it comes here. Router will never send it out anywhere. It will not propagate broadcast messages. Okay, it will. So they only broadcast can be only sent within the same subnet. Never go. Never pass the router. Router is router is actually used to divide your subnets. If you need to divide it, you put a router in the middle, and it will split your network into two subnets, and they will become two independent subnets. So the broadcasts will reach the router and not pass the router. Yeah. So when device receives a broadcast, it can see that it is broadcast because it will have all ones as a destination, and it will process it. Yeah. If it receives a frame which is not meant for that device, it can compare the MAC address of the destination with its own MAC address, and if they don't match, if it is a unicast, it will just drop the frame. But if it is a broadcast, it will accept it. It will process the frame. Yep, all the broadcast frames will be processed by everyone, by every device. Now, there is something which is called multicast. And multicast is when the message is meant to not for all, but more than one. Yeah, not just well, it can actually go to one, but it's not limited to one like unicast. But it's called multicast. It doesn't work with IP version 4, but it is available in IP version 6. So in IP version 4, it's not available, but in IP version 6, it is. And oh no, sorry, it's an ARP, yeah, but it is available for all other. Sorry, my bad. Yeah, multicast it can be done in IP version 4, but it's for different not for ARP protocols. I was thinking about ARP. Yeah. So it can be, yeah, it is available for IP version 4. Yeah, I was thinking about ARP. Yeah, all right. Yeah, so it will look like, yeah, in IP version 4, it looks like this. What I meant, why I'm because in IP version 4, it's not very popular. It's not very common, but in IP version 6, it's the only one. So in IP version 6, broadcast is not available. So they are replaced by multicast in IP version 6. Yeah, that's what I meant. And IP version 4 will use unicast and broadcast most of the time, and multicast kind of, yeah, sometimes. Yeah, not very popular. So IP version 4 multicast will look like this. Yeah, so when you see the in destination MAC address, when it looks like this, that is a multicast. And for IP version 6, that's how it looks like. Yes, so the destination will begin with 3333, right? Remember, these are hexadecimals. There are other reserved multicast destination MAC addresses for when encapsulated data is not IP, such as spanning tree protocol. Yes. Yeah, so we're going to look at spanning tree protocol at some point. Yeah, multicast. All right, so yeah, yeah, so the spanning tree protocol is a way of it's like a service protocol. Yeah, it's not something which you use in communication between devices. These are devices talking to each other just for service, to exchange some servicing information with each other, right? Kind of. It is flooded out of all Ethernet ports except the incoming port, unless the switch is configured for multicast snooping. Yes, so the switch, when this is a switch, so when it comes in, if there is anything that is connected, it will go out, right? Like broadcast. Yeah, so it will go out of every port that is connected to the switch, excluding it's not going in backward, except the incoming port, because it, again, doesn't make sense. Why would it send it back? And this is a special case. The switch can be configured for multicast snooping. We are not looking into this. This is beyond this CCNA altogether. And also, multicast will not be forwarded by the router like a broadcast. Yeah. So if there is a router, it can come to the router. If it is a default gateway, and then it won't go any further. The router will not propagate it. Unless the router is configured to route multicast packets. So you can you can configure it to make this exception if it is needed for some configuration, kind of exchanging configuration between routers, for instance. Then it can pass on those multicast packets. It needs a special configuration, not by default. Because multicast addresses represent a group of addresses, sometimes called a host group, they can only be used as the destination of a packet. Again, yes, so like the source will always be unicast. Same principle applies. As with the unicast and broadcast addresses, the multicast IP addresses require a corresponding multicast MAC address. Yeah, so if it is a multicast IP, it needs a corresponding multicast MAC. Yeah, so if it is a group, so you can see it's a group. It will have a multicast IP, and then it needs to have a multicast MAC address like that. So it will begin with this sequence, and then this part can be used to identify different groups.
Yeah, Pavel, this is my question. Like, in that case, how do you identify this? The one with the tick mark. So it's been differentiated by the last three hexadecimal IP addresses, I guess. That's what you
So
meant, right?
in hex for multicast addresses will be anything beginning with 224 and up to 239. They are not assigned. They are not allowed to be assigned to any devices. Yeah. So you can see here. So it's a special kind of separated group, not separated, but kind of dedicated group of addresses, which can only be used for multicast.
Yeah, it has to be done by individual, the PCs or the
No.
devices.
So it's usually, so for instance, there is a protocol which will be used by routers to exchange information about routing. Yeah. So one router needs to send information to another router, and it is not meant to reach PCs, devices, or anyone but just routers, right? So for this case, there is a multicast group, because it will go to all routers, but no one else. And this will be pre-configured. It will be predefined. So this router, if there is like a protocol called OSPF. So all routers which will be configured with OSPF protocol, they will send all these multicast messages to 224.0.0.5, yeah, and or 1 So this will be reserved for special group of routers, which will belong to special protocol, right? So or 2 or 9, yeah, or 5. It's not something you can assign. So when you put this router, when I configure it with OSPF, it will start using this protocol as a multicast. Yeah.
Okay. So in this case, like, you know, in this topology, you should have a, I mean, they should have a the router in between before in these devices, right? Between these devices. I mean, switches and the devices, destination devices.
Switches don't use IP addresses. So, but only switches don't understand IP, but only router. So router, if it wants to send reach all the routers, all OSPF routers, it will send a message to this specific reserved IP address, and only routers which are configured with OSPF protocol will receive it and process it. Others will not receive this message. That's the purpose of multicast.
Okay, thank you.
Lab view network devices MAC addresses. So this is a lab. We're not going to do it. Yeah, so it's a lab. So you can set up topology, initialize devices, configure devices, and verify, display, describe, and analyze Ethernet MAC addresses. So again, it's the same story like we did in Wireshark. Yeah, but we're not going to do it. We doing it online, and it's not, and it's not needed. Basically, it's just to show you what MAC address is. Right? We kind of looked at it in Wireshark anyway. It's not something really useful. Just I don't think so. Yeah, and so we've got something. We've got quite a few slides still left. 4 minutes before 1. So I think we're not going to start switching before the break. Okay, we'll do it after the break. We'll begin this, and I think we will finish it today. It shouldn't be a problem. So, guys, I suggest we take a break, and we'll come back at 2 o'clock. 1 hour break. Okay, everyone.
Pavel, you still around?
I am, yes.
Hey, just a quick question about the lab you mentioned about the previous one, 7.27. So I think try that one with the Wireshark. We need a switch, like a, I mean,
No, you
the
can't do it.
home lab or something. Yeah, home lab or something, right?
Yes.
Yeah, got it. Yeah, thank you.
So you need to connect, set up a topology.
Yeah.
It's not possible online. But I don't think it's needed, to be honest. I mean, you can try to do it in packet trace if you want. I think this is possible.
How do you connect Wireshark to that one?
You can't.
Yeah, that's the thing.
No, you can't connect Wireshark to packet tracer, but you can. In packet tracer, there is a simulation. So in packet tracer, you can view things like similarly like in Wireshark. You can do it in packet tracer. You can't use Wireshark, but you can. There is built into packet tracer part of packet tracer which functions as similar to Wireshark.
Wireshark. All right. Yeah. Got it. Thank you.
Yeah, you can try. You can try if you want to, but as I said, I don't think it's really useful.
Yeah, it could be like something like if you want to
like a challenge for you.
Challenge, yeah. Yes, thank you.
Okay. See you after the break. Yeah, in 1 hour after at 2 o'clock, please.
Okay, see you at 2, Pavel.
See you. can use MAC addresses to deliver messages, right? And how they operate. So, switch fundamentals. Switch operates at a layer 2 normally. There are some exceptions. There are some later on, but in the beginning, when switch was created, it was meant to operate at layer 2. Layer 2 means it operates with MAC addresses. Sorry, where is this? And so switch will not understand IP addresses. Switches are not designed. I mean, generic switches, just normal switches. Yeah, there are some exceptions. You will look at later on, but in general, the switch that we use in just typical switch, we use, and it won't understand IP addresses. It doesn't need to understand anything, any above layers. So it only operates at layer 2. Right, whatever happens above, it's not aware of that. So the switch will make its forwarding decisions based solely on layer 2 Ethernet MAC addresses. So where it needs to go, the destination MAC address, and the source MAC address, it will play part as well. So when frame comes to the switch, and it will look at its own MAC address table. This is like a list of MAC addresses. It will, which will be known to the switch. So and it will consult MAC address table and make a forwarding decision. So it will, if it is on the list, the destination, it will send it directly to the where it needs to go, to the destination. Yeah, but MAC address table will be only populated if there is a repeat message which was already delivered by the switch. So initially, when the switch is turned on, MAC address table is empty. There is nothing. So switch needs to populate the MAC address table. So that list, yeah, so of MAC addresses which are known to the switch, right? And then all the forwarding decisions will be made by consulting this MAC address table. Sometimes MAC address table is called content addressable memory. So you will see something which looks like CAM table, right? So it's kind of MAC CAM. That's the reverse, if you like. It means different things. Yeah, remember, MAC is media access control, and CAM is content addressable memory, right? Which means basically this table, right? So you've got MAC address. So how the table will look like: MAC address and a port. So port number of the switch. So port number 1 has this particular MAC address. Port number 2 will have another MAC address, and so on. So you can call it CAM table, you can call it MAC table. It means the same thing. So switch will populate its MAC table or CAM table, MAC table, by looking at the source MAC address, right? Not destination, because destination, it can be, I mean, just imagine switch, and this is a switch, right? And it has a device here, device there, right? So this is port number 1, this is port number 2, this is port number 3. This is MAC address A, MAC address B, MAC address C, CC, BB, AA. Yeah. And so AA PC, let's call it PC1, PC2, PC3, 3. PC1, which has MAC address AA, wants to communicate with MAC PC3, which has MAC address CC. So it will send a message, and it will come on looking from the switch perspective. So switch will receive a message on port 1, and it needs to go to MAC address CC. Switch will consult its own MAC address table, and if it doesn't know where CC is, like if it's just switched on, or maybe there is no communication happened within previous 5 minutes, because it will keep track of that MAC address table for 5 minutes, for 300 seconds by default. And so if there is no entry for this MAC address, so the switch will forward it everywhere. Yeah, so it will forward the message to every device that is connected at this moment. So it will go to PC2 and PC3, because at this moment switch doesn't know where to send it. But what it will use this message to the source where it comes from. It will use to populate its table. Yeah, because so now at this moment, before the message is received, the table will contain MAC addresses and port numbers, right? So these are the links. So the port at this moment, it's empty. When the message comes from PC1 with AA as a MAC address of that device, so the switch will learn that on port 1 there is a device which has a MAC address AA. It doesn't know that it is a PC1. It doesn't know what it is. It doesn't matter to the switch. All it knows that there is a device which has a MAC address, right? So the MAC address AA will be associated with port 1 for next 300 seconds, for 5 minutes. Okay, so this switch will be this way. The switch will be able to populate the MAC address table. So and then when the switch will forward this message to PC2 and PC3, because it doesn't know where this device CC is. So remember, this goes to AA from it goes to CC from AA. Yeah, and it comes to the switch. It doesn't know where CC is, but now it will know that AA is associated with port 1. It is on port 1 where AA is located. And when the message is delivered to PC2 and PC3, PC2 will receive it as well as PC3, but PC2 will check that the destination MAC address in the message against its own MAC address, and it will discard the message because it's not addressed for PC2, right? So message will be received here and it will be discarded. But PC3 will accept this message because it is meant to be delivered to PC3, right? It will accept the message, process it, and most likely it will reply, right? When it replies with its own now message, right? And that message will contain, it will be replied to AA, to PC1, right? So AA will be destination, CC will be the source. When it comes on port 3, now switch will establish that on port 3 there is a device which has a MAC address CC, and it put this binding into the MAC address table. Yeah, this association, and when the message comes on port 3, it will populate its MAC address table and consult its MAC address table for it will look for the destination AA. And AA will be already there because from the previous exchange, the MAC address table was populated. So now the switch will know that AA is on port 1, And so this message, when it goes back to AA, will be delivered straight to AA. It won't be sent to PC2 because yes, Switch now knows how to deliver it directly to PC1, to not PC1, to AA, address AA. Yeah, and that's basically the mechanism. Yeah, so nothing fancy, but the principle is yeah, it's a quite simple principle. If for instance for some this like if there is something changed and there's another device now on this port, right? So on port 3 you connect a different device. It's still a PC, but now it has a different MAC address, different device, right? And so, but the MAC address table will contain CC. It will link CC MAC address to port 3. But now we've got DD. So when basically the communication will happen with DD and switch will just update, it will delete this entry and it will update. So now DD is on device with MAC address DD is on port 3. That's all. Okay, is it? So so first it will learn, right? And then it will forward, find destination. If the destination MAC address is a unicast address, the switch will look for a match between, this I described only unicast messages, right? If it is a broadcast, obviously the switch will doesn't need to consult its MAC address table. It will just broadcast it out of every available port. So if it is a unicast address as a destination, not broadcast, then it will go through this process. So it will look for a match between the destination MAC address of the frame and an entry in the MAC address table and blah, blah, blah. And then it will forward it out to the specified port. If it's not in the table, the switch will forward the frame out all ports except the incoming ports. This is called unknown unicast. So yeah, so it comes to the switch first. Remember in the beginning, this PC. So it comes to the switch from here, from AA to CC. This is CC still, yeah. We changed it, so it comes to CC, and switch doesn't know where CC is, so it will send it every available port, but not obvious. It won't send it back because there's no need, right? So it will send it out of all available ports. This is called unknown unicast, but in essence, it is equivalent of broadcast message. Yeah, so because it goes out every available port. But the reason why switch does it, it's because it is unknown unicast. It is a unicast message, but it is unknown. If the message is broadcast or multicast, the frame is also flooded out all ports except the incoming port, right? So unknown unicast, broadcast, multicast, message gets flooded. It's called flooded as well. Yes, so it's flooded out all ports. If it is a known unicast, then it will go to a specific destination. If it is, so the entry is present in the MAC address table, then the switch will know where to send it directly, a unicast. It won't flood it all out of all ports. So, filtering frame. As switch receives frames from different devices, it is able to populate its MAC address table by examining the source MAC address of every frame. When the MAC address table of the switch contains the destination MAC address, it is able to filter the frame and forward out a single port. Right, so A sends something to D, destination is D, comes from A. And so after exchange, right, well, it looks like the MAC address table is already populated with this binding. Yes, so port 1 is on port 1 there is a device which has this MAC address, right? And on port 4 this MAC address. So switch will know. It won't flood anything. It will send them directly from A to D and D to A. Yeah, it's already known. Okay, it looks simple, but people get sometimes confused. So let's watch a video. Let me find it, and it will just reiterate everything. Right, so this is a connected switches, right? So this is, well, you can call it a complication if you like, but basically, if there are two switches, right, which are connected, right? Switch 1, switch 2, and this is A, this is B, and this is C. PC3, PC2, BB, CC, and a PC1. PC1. Right. So if PC1 wants to communicate with PC2, sorry, with BB MAC address, right? So the switch one will send it. So there's a port 1, port 2, port 3, port 4, port 5, right? So, well, it's not the same because they're not this is not sequence. So, but just for convenience, but you understand that ports will be okay. Let's say this is 3, 4, and 5, just for convenience. So AA will send something to BB, PC1 to PC2. Switch 1 will send it out of its own port 2, because this is the only one that is connected here, right? Isn't it? So this is incoming, and there is only one outgoing. Or maybe we can, let's say there is another device, we call it PC4, and it has DD, right? So let's say switch receives it on port 1, and this is port 6. So switch will send it, if it doesn't know where it needs to go, so it will send it out of all ports, flood it out, right? So it will go to here, and it will go to there, to the next, well, out of this port, port 2 of switch 1, isn't it? Well, eventually it will reach PC2 with MAC address BB, right? This is what we're sending. So we send to BB from AA. So BB will be reached, BB will reply, and it will send it back, right? So switch 2, first of all, switch 2 will learn that there is a device with the MAC address AA, and it will associate it with port 3, isn't it? So we're talking about MAC address table of switch 2, MAC port. So when it comes to message from AA, from PC1, comes to we're looking from perspective of switch 2. So switch 2 will receive something on port 3, and there is a device AA on that port, right? And then there is a separate MAC address table of switch 1, same story, MAC address port number, right? So when there is a reply from BB, from PC2 back to PC1 on AA, switch 2 will send it there, right? And now switch 1 will recognize that on port 2 port number 2, there is a device which has an address BB, right? And it will deliver it to A, let's say. Then AA wants to communicate with PC3 here. PC1 wants to communicate with PC3. So it sends something to CC. And again, switch 1 will not know how to deliver it. It will send it to PC4. It will flood it, right? And it will send it. Out here and out there, right? Switch 2 will receive it, and again will send it everywhere. And then CC will reply. Oh yeah, sorry. Before we do this, switch 2 will receive it on port 3 again. And all right, sorry, it comes from AA. Okay, doesn't matter. Yeah, it's not going. There's no need to update. All right, leave it. Sorry. So switch 2 receives something on port 3 from the same device, AA, and it needs to deliver it now to CC. So it will flood it all ports, and when it receives a reply from CC back, it will update its CAM table, MAC table, and it says now CC is on my port 5, isn't it? And also BB will be there as well, because we remember the previous communication was there. So on port 4, there is a BB, right? So this is the MAC table of switch 2. And now it sends it back, a reply from CC, back to switch 1. And now switch 1 will update its own MAC table. And on port 2, there is another device, CC, isn't it? It comes from this device. Yeah? So you can say that, yes, so what happens? So on the same port, there are multiple devices. So it will keep updating. That's what it is. Yeah, when we have connected switches. And that's what we're going to be in that video. Let's have a look. I need to share sound.
In this video, PCA is going to send an Ethernet frame to PCB, and PCB is going to send an Ethernet frame to PCA. We're going to examine how switches S1 and S2 build their MAC address tables, and also how they forward frames based on the information in those MAC address tables. PCA has an Ethernet frame to send to PCB. The source MAC address of the frame is 000A and the destination MAC address is 000B. The Ethernet frame is sent to switch S1. S1 receives the Ethernet frame, examines the source MAC address, and notices that this MAC address is not in its MAC address table, so it adds the MAC address and the incoming port number. Next, switch S1 examines the destination MAC address and notices that this MAC address is not in its table, so it floods it out all ports. PCB receives the Ethernet frame, examines the destination MAC address against its own MAC address, and notices that that is a match and receives the rest of the frame.
Sorry, I'll rewind it. I think it was here.
And notices that this MAC address is not in its table, so it floods it out all ports. PCB receives the Ethernet frame, examines the destination MAC address against its own MAC address, and notices that that is a match and receives the rest of the frame. The Ethernet frame continues to be forwarded to switch S2. Switch S2 examines the source MAC address of the frame and notices it is not in its MAC address table, so it adds the MAC address and the incoming port to its MAC address table. Next, switch S2 examines the destination MAC address, notices that is not in its MAC address table, so it floods it out all ports. PCC receives the Ethernet frame and its MAC address does not match the destination MAC address of the Ethernet frame, so it does not accept the rest of the frame. The router receives the Ethernet frame, examines the destination MAC address against its own MAC address, and notices it is not a match, so it does not receive the rest of the frame. Now let's have PCB sending a frame back to PCA.
So you can see, even though switch 2 didn't deliver the message at all. It was meant to be delivered to PCB, but it still updated its MAC address table, yeah, because it did receive the frame, and it just put it in the MAC address table, its own MAC address table. That on port 1 there is a device which has MAC address 0001A. Yeah.
The source MAC address of the frame is 000B, and the destination MAC address is 000A. PCB sends it to switch S1. S1 notices that the source MAC address is not in its MAC address table, so it adds the MAC address and the incoming port number. Next, switch S1 examines the destination MAC address and notices that MAC address is in its MAC address table, so it sends it out just port 1. PCA receives the Ethernet frame, examines the destination MAC address against its own MAC address, and notices it is a match, so it receives the rest of the frame.
Right. So I hope it was useful. Yeah. So now, yeah. So there is another video which will explain how the message will be delivered to default gateway now. Is it wrong? So I think it's wrong. So give me a second. Yeah, it's the next video, not this one. There you go.
In this video, PCA is going to send a packet to the internet because the destination IP address is on another network. So in this case, the source MAC address is that of PCA. The destination MAC address is that of the router of 000D. So
why is it of the router? Because we watched in Wireshark. Yeah. So the MAC addresses, if the destination is outside of the local network, it is on remote network. So everything has to be sent to the default gateway, right? To the router. So the MAC address of the router will be the destination.
Ethernet frame is sent to switch S1. Switch S1 receives the frame, examines the source MAC address, which is in its MAC address table. So it just simply refreshes the 5-minute timer. It examines the destination MAC address.
Yeah, and this is important. Sorry. So when there is a second communication now on the same port, there is no need to update the MAC address table. Yeah, because it comes from the same MAC, from the same PCA on port 1, which as in previous communication. But what happens? It will update the timer. Now it will reset it to 0. No, not to 0, but 300 seconds again. So previous might have happened a little bit earlier, but now it will reset the timer back to 5 minutes. So it will start countdown from 300 seconds down, yeah, to 299, 298, and whatever until it reaches 0, and then it will just drop. If there is no communication during these 5 minutes, it will delete the entry. But if there is a new communication, it will reset the timer again to 5 minutes, and again to 5 minutes, and again to 5 minutes. Yeah.
Address, and because that destination MAC address is not in the MAC address table of switch S1, it floods it out all ports. PCB receives the Ethernet frame, and because the destination MAC address does not match its own MAC address, it does not accept the rest of the frame. Switch S2 receives the Ethernet frame, examines the source MAC address, which is in its MAC address table, so it also simply refreshes the 5-minute timer. It examines the destination MAC address of the frame, which is not in its MAC address table, so it floods it out all ports. PCC gets the Ethernet frame, and because the destination MAC address does not match its own MAC address, it does not accept the rest of the Ethernet frame. The router receives the Ethernet frame, and because the destination MAC address does match its own MAC address, it accepts the rest of the frame. Now we'll look at the Ethernet frame coming from the router back to PCA. The source IP address is the IP address actually of a device on a remote network. The source MAC address is that of the router at 000D, and the destination MAC address is that of PCA. The frame is sent to switch S2. S2 receives it, examines the source MAC address, which is not in its MAC address table, so it adds it. It then examines the destination MAC address, which is in its MAC address table, so it forwards it out port 1. S1 receives the Ethernet frame, examines the source MAC address, which is not in its MAC address table, so it adds it to its MAC address table. It examines the destination MAC address, which is in its MAC address table, so it goes ahead and just forwards it out port 1 towards PCA. PCA examines the destination MAC address, and because it is a match, it accepts the rest of the frame.
All right. So, yeah, just remember. So, if there is a new communication, it will the on the same port with the same MAC address, which happened in the previous 5 minutes, then the timer will reset. But if there is no entry, it will be just populated. The MAC address table will be, the entry will be put there. Yeah. So yeah, so you can view on the switch, so you can view some MAC address table. We'll do it later on in the packet trace at some point. Yeah. There is an activity that which is really useful. We can you can do it, and let me just find it. Okay, so it's called activity switched 736, right? So let's do this. What's going on? Why is it doing this? I don't understand. Supposed to. Anyway, here. Okay, yeah. Sorry. Yeah, my bad. So we've got this activity. So the aim here is to determine how the switch forwards a frame based on the source MAC address, the destination MAC address, and information in the switch MAC table. Answer the questions using the information provided. So we've got a frame which goes to destination MAC address OA, right? Goes to OA from OC. Yeah, so OC is sending a frame to OA. And MAC address table contains this much information. So it knows that OC is on FA5, yeah, fast Ethernet interface, port number 5. And also it knows about D and E, but it doesn't know where A is. So the destination is A. So because it doesn't know where A is, yeah. So what is going to happen? There are two questions for each. So here, where will the switch forward the frame? Based on information that is given, so it goes from C to A, and MAC address table doesn't include entry for A, for the destination. So the first question is, where will the switch forward the frame? Okay, any ideas?
Pavel, I think it's going to forward it to port 1, port 3, port 7, and port 9.
Port 7 and port 9. Yeah,
So
it looks right
port
to me,
1,
yes.
Port 1, 3, port 1, 3, 7, and 9.
Yeah, it looks right to me. Yeah, everyone agree? Yes. Yeah. Because it will forward out of all ports except the incoming port. Yeah, so incoming is 5. So it will have to it has to send it out of 1, 3, 7, 9. It looks correct to me. So question number 2. When the switch forwards the frame, which statements are, yeah. Switch will know if there is something attached to that port. Yeah, if there is nothing, it will not do anything. It will be just, yeah, it won't send out of port which is not connected, right? So,
And that includes being that the other device has to be switched on as well. So it may have something connected, but if it's not powered on, then it's not going to receive anything either.
of course,
No activity.
yeah, this is given. Yeah, absolutely. If you just plug a cable in it and there is no device which does something, yeah, it won't matter. All right, so question number 2. When the switch forwards the frame, which statements are true? So let's do one by one. Switch adds the source MAC address, which is currently not in the MAC address table. Is it true? Looking at the current MAC table, does it need to add MAC address of C to its current MAC table?
No.
No. Yeah, because it's already there. Yeah, C is already in the MAC table. Now, frame is a broadcast frame and will be forwarded to all ports. No, it isn't. It's not a broadcast. It goes to A. Yeah, it's not a broadcast. So this doesn't apply. Frame is a unicast frame and will be sent to specific port only. Do you think so?
No.
Or there are other options. Frame is a unicast frame and will be flooded to all ports. Or frame is a unicast frame, but it will be dropped at the switch. So which out of these 3 last ones do you think will apply?
I think it's the second to last.
This one? Yeah. Yeah, because A is not known to the switch, so it has to be flooded out of all ports. Yeah? Yeah. So let's check. Yeah, correct. Beautiful. Now we can have a new problem. So there's a endless bunch of problems, so you can enjoy it to your heart content. Yeah, at home. So now we've got a frame which goes to E from F. F is the sender. Oh, yeah, okay. So by the way, this little device that is connected to the switch on port 9 is a hub. Remember hub? Hub is a old device. Yeah, it's like a dumb version of a switch. It has multiple ports, but it always floods everything out of every port connected. It doesn't have any intelligence. Hub is like a device to which multiple devices are connected, similar to switch, but it doesn't have any intelligence. It can't distinguish whether it needs to go this way or that way. It just it just floods everything regardless. It just floods out of every connected port. That is what hub does. Yeah, and hub is a half duplex. Remember, it's not full duplex, half duplex device. Yeah, so this is an example of that. It's a kind of a complication of sort. So, so the message is from F to E, and MAC address table does contain F and E, by the way. So F and E are actually on the same port. Well, how lucky you are, guys. Usually it's very difficult to come to this, but you got it on the second attempt. So yeah, from F to E, and yeah. So what happens? Question number 1. Where will the switch forward the frame?
I think it's to every single one connected port, including. So I think 1, 3, 5, 7, and also to.
But why? Doesn't
Because
it
it
know
doesn't.
where E is? The destination is E, and it already knows where E is, isn't it?
But
It
because
is.
it's a hub, and you said it's dumb, it's going to send
No,
back
we're
to
talking about
everything.
switch. The
Ah,
question is, where will
oh,
the switch forward the frame, not hub?
oh, sorry.
Yeah, the question is about switch. Hub is there, yes, but hub will do what hubs do, but we're talking about the switch.
It forwards
So,
on itself now.
well,
Right.
yeah, well, because it comes from F on port 9, and it goes to E. So where do you think it will go? Will it go?
9.
Will it go back to 9?
Yeah.
Just do 9. Yeah. Is that separated? Is that closed off like a virtual LAN?
No. It's not.
F9 to 12.
No, it's not. No, there are no virtual LANs here. No.
Why is there a little split, a divide in between the hub? The
Well,
switch,
hub.
sorry, the switch. So not the hub, the switch.
This is a hub.
Yeah, I know, but above
Yeah.
it, just above there, there's those 4 F to 12 seems to be there's a divider.
No, it doesn't matter.
Just in
It's
between.
just nothing. It's not. Doesn't matter. No, nothing. It's
No?
nothing. Yeah.
Okay.
It doesn't mean anything. No. So. Okay, so we think it will go to the switch will send it to 9, right? Forward it to 9. When the switch will add. So question 2, switch will does this apply basically? Probably not. Yeah, because switch already knows where F is. It's here. It knows in MAC address table, it contains the entry for F and for E. So there is no need for switch to update anything, right? It's not going to update its MAC address table. There's a background noise coming from someone, I don't know, radio, TV or something, guys. Yeah, someone, I don't know who this is. I think it's Samuel. Second, does this apply? Frame is a broadcast frame and will be forwarded to all ports. Well, it isn't. It goes to E, right? And it's not a broadcast. Frame is a unicast frame and will be sent to specific port only.
I think it's that one.
Yeah. Well, I think it's a tricky question because of the hub. Yeah. Let's. So the question is, because hub will deliver it to E anyway, right? What happens? So when it comes from F and it reaches hub will send it to E, and it will also send it to F9 on the switch, right? It goes because it just broadcasts everything, the hub. So so this is a bit tricky. So I think what is going to happen is probably this, but let's see. Yeah, so this is the correct answer, you see? So show me. Oh, it doesn't apply. It doesn't. Why doesn't it? Okay.
You need to
Sorry.
one, then it will be able to.
So what is happening here? F is connected to the hub, not to the switch directly, to hub. That hub will broadcast that message. It will send it to E and to the switch, to port 9 of the switch. So the message will be delivered by hub. So I believe the switch will just drop it. But why can't we reset it? There's a yeah. I clicked on show me and it did show this. So that's what it looks like to me. That's what is going to happen. Yeah. And port will not send anything back to the on the same port. Remember? So it came on 9 to the switch, so it won't send it back. All right. So it's a bit tricky. Okay. It's a bit because of this hub inclusion of the hub, and it is a bit tricky.
So Pavel, so the
Yeah.
question 1, there's no answer for it, or for the
It
question 1?
It won't forward it anywhere. It will just drop it.
I'll
Yeah.
drop it. Yeah.
It comes on the same. It comes on the same port, and it needs to go out of the same port because switch knows that destination and the source are on the same port 9. It is in the MAC table, isn't it? It's already there. This information, so the switch will drop it. It won't. There's no need to send it anywhere.
The problem is I can't check the answer whether correct or not without clicking question 1. If you know what I mean, they can't check. If you check, then the check is available, I think.
No.
For me, no.
No, because I clicked on show me and it did show this. The last option was there. You don't need to click on because if the switch drops everything, so there is no need. You don't need to check anything here. You don't need to tick any of the questions or of the options. Okay, it's a bit tricky. Okay, so it's kind of fortunate or maybe unfortunate that we came across almost immediately when after starting this. Anyway, so new problem. Have a look here. So goes to E from D, right? From to E. E is known to Mac to the switch. It knows it is on 9, so it will send it directly to out of 9, isn't it?
Yeah.
So it is a unicast frame, and it will be sent to specific port only. And does it know where D is? No, it doesn't. So it will also update its MAC table because it doesn't know where it comes from D, but it's not in the MAC table, is it? So we can check. Yeah, correct. Oh, the previous check didn't work for us. Yeah, all right. Yeah, maybe you're right. Something wasn't right in the previous question. Check wasn't available. It was just new problem and that's it. But I think because I clicked on show me. So if I click on show me, check becomes unavailable. Yeah. If I click on show me, check is grayed out now. Because it is the answer is revealed to you. Okay. So new problem. So look, show me. That's it. You can click on show me, and it will show you what is the. And now you can change it, but it doesn't change anything, right? So you need to go to the new problem now. So new problem. Right, from E to B. From is B present in the MAC table? It is. So so it will have to be sent out directly port 3. And does it need to update its table? It comes from E, and E is in the table, so it doesn't need to update it. So it is a unicast frame and will be sent out specific port only. Check. Correct. Yeah. So you can play with this as long as you want. Right? It's quite interesting, I think. All right, and so we've got 10 minutes, and we need to talk about switch speeds and forwarding methods quickly. I think we can do it. So switches, when they receive the frame, like we watched in the previous exercise, yeah. So the switch will receive a frame, and it will know, it will read the destination, and it will send it on to the destination or flood it out, whatever, if it is unknown unicast. So default behavior, well, it's not default, but it's how it all began, I guess. So store and forward switching, right? So the switch will receive the entire frame, including the trailer, the last bit of that frame, which means it will receive the frame check sequence and that error detection part of the end of the frame, right? And this will allow the switch to do the corruption checks, yeah, if it is corrupted or not, because it will allow entire frame to be read, right? So it will receive the entire frame, including the end of it, the trailer, and it will be able to check if the frame has been corrupted or not. And it will check the destination address, and it will make a decision, so where it needs to go, if it is unknown unicast or broadcast or whatever, or if it knows where to send it out, which port. So, but this method requires the entire frame to be read, and it takes a bit of it takes a little bit longer than if you choose a different method, which will allow to read only the destination address and make decision straight on. Yeah, so you read the destination and you send it on straight on. Yeah, so the switch will not wait for the entire frame to be received before making the decision. So this allows quicker decision making. Yeah. So the destination address will be read, and then the frame will be forwarded. So this gives a big advantage in this. For the store and forward, for the first method, for this, the big advantage is that it determines if the frame has errors before propagating the frame. So if there is an error, it will drop it, right? So no frames which contain errors will be sent on, right? So it will reduce the amount of bandwidth consumed by corrupt data. Makes sense. But because of this longer decision making, it may be not kind of preferred method. So the store and forward switch. Oh, sorry. Yeah. So, but still talking about store and forward. Store and forward is required for quality of service analysis on converged networks where frame classification or for traffic prioritization is necessary. All right. So later on, we're going to talk about something which is called quality of service. So you can prioritize certain traffic. Certain kind of traffic over the other, give it a priority. So if this is the case, then so you can use it, store and forward. It is required, right? If quality of service is in place, if it is there. So, for instance, voice over IP data will need to have a highest priority over web browsing. Yeah. So in this case, if the quality of service is in place, then you have to choose store and forward. You have no choice. But if it is not, if you don't have quality of service, and then you can cut through. You're going to use cut through, which is also in its turn is split between two kinds, yeah, two methods. So one is fast forward. This is basically a little bit reckless if you look at it, because it just reads the destination and sends it on without any care for checking for corruption or anything else, right? And yeah, so because it starts forwarding before the entire packet has been received, there may be times when packets are relayed, forwarded with errors. Obviously, it's not ideal. And then the destination network interface card we have to deal with this error, corrupted frames and drop them. Right, so the bandwidth will be still kind of occupied. So, but it's not like it happens often anyway. So there's errors. But for instance, if there's some sort of a problem with the source where they come from, and the source might produce lots of corrupted frames, and then obviously it becomes an issue. But it's not often that this happens. Some errors. And also you can configure the switch to use fragment-free switching. And so because with this, the fast forward, you read the destination, and remember the destination is 48-bit long. MAC address. Yeah, MAC address is 48-bit long. So you read, you allow the switch to read 48 bit only, right? And then, which is 6 bytes, yeah, 6 bytes. And immediately the frame will be forwarded. But if you remember from when we're talking about the frames, so the anything that is less than 64 bytes considered to be, if it is less than 64, it's a runt frame, yeah, and they have to be discarded. So these are definitely not okay. If the size of the frame is less than 64 bytes, it's not okay to send them on.
That
So
chevron should be the other way, Pavel. If it's less than, no? That chevron should be
yeah,
the
sorry,
other way.
yeah,
Greater than.
probably like that, yeah, less than 64 bytes, yeah. So fragment-free switching, a compromise between the high latency and high integrity of store and forward. So you basically here you are allowed to read first 64 bytes with this one. So at least this will exclude the possibility of sending runt frames on, and that means that usually you will be excluding all the erroneous frames. Yeah. So because the most network errors and collisions occur during the first 64 bytes. This is the nature of the of networking. So if you allow first 64 bytes to be read, and it almost it won't guarantee anything, but it will exclude most of the erroneous frames. Okay, so cut through can be done in two ways: fast forward and fragment free switching. it is your side usually it's you don't mess with this. So why would you set half duplex? But if for some reason one end is set to half duplex, then the other end has to be half duplex as well. Yeah, because if one end is set to half, it will there will be some problems with transmissions. It's usually auto-negotiated, yeah, and on most Ethernet switches and network interface cards. So two devices will automatically negotiate the best speed and duplex capabilities. So you shouldn't mess with any of that. So, and also beginning with gigabit Ethernet ports, they can only operate with full duplex. So half duplex is only available for Ethernet and fast Ethernet, which are 10 megabits and 100 megabits per second. Beginning with gigabit, only full duplex is possible. But if basically it's just it is only it only concerns old kind of setups, yeah, old equipment of some sort. So you might come across something like that, and so yeah, if one end is full duplex, the other one is half duplex, it's going to be a problem. Yeah, so the duplex mismatch is one of the most common causes of performance issues on 10/100 megabits per second Ethernet links. This can occur when one or more or both ports on a link are reset, and auto-negotiation process does not result in both links having the same configuration. So basically, auto-config will fail for some reason. And it also can occur when users reconfigure one side of a link and forget to reconfigure the other. That's why you don't need to. You really shouldn't mess with this. Both sides of a link should have auto negotiation on, or both sides should have it off. Best practice is to configure both switch ports as full duplex, right? So you just configure it manually, full duplex, and that's it. Auto MDIX. This is to you remember the straight through. Yeah, crossover and straight through. Okay, it's all here. Straight through cable, right? More recent devices, they will all have auto MDIX. So they will be able to adapt themselves automatically. Regardless of which cable you use, is it crossover, straight through, they will sense it and they will internally change the circuitry, right? So the order of those connections. Remember from physical layer, we remember the Ethernet, so some crossover straight through cable. Direct connection between a router and a host requires a crossover, and also similar devices, yeah, PC to PC crossover, switch to switch crossover, router to router crossover. But configure the interfaces accordingly. It is enabled by default on switches running Cisco iOS release 12. So it's kind of quite long way back. Yeah, 12.2, I think it's. It was introduced MDIX, yeah, auto MDIX. But it could be disabled. Yeah, so for this reason, you should always use the correct cable type and not rely on the use a straight through cable and rely on Miracle. What if MDIX fails? Then you have a problem. It can be re-enabled. Anyway, am I talking to myself? That's.
I think his mic